Later you are using. Later.
Later. Okay, thanks. Okay, good morning. Today I thought I'd do a little work on the board, sort of mostly to slow the pace down, and also try to get across more of an idea of why, what the purpose of this course of lectures is really. See, a lot of statistical mechanics or statistical physics does not actually bother about the individual dynamics of any particular constituent in the group of whatever it is considering, right? So when you want to discuss, for example, the thermodynamics of the air in this room, we're not actually bothered about the individual motion of each of the molecules, and we don't really care about them, but we make a few assumptions. One of the strong assumptions that we make is that things are ergodic, all right? So the ergodic hypothesis, which is usually stated as time averages equal to space averages or ensemble averages, is a hypothesis. It's very, very likely to be true. One sort of cannot imagine it not being true. But at the same time, there are very few systems for which you can explicitly show that it is, in fact, correct. One of them is the system that I sort of very briefly talked about yesterday, which is the rigid rotation of the circle, where theta goes to theta plus alpha mod 1. So you'll just get points on the circle. The circle has got circumference 1, let's say. And so if you start with some initial theta naught, you can sort of easily convince yourself, work it out, that if alpha is rational, the points will recur, and if alpha is irrational, the points will not recur. But this system is explicitly ergodic, because given sufficient, so you start with some theta naught plus alpha, etc., and in the limit of theta naught plus n alpha mod 1, n going to infinity, every point on the circle would be covered. So this is an example of an ergodic system. It's not a very interesting ergodic system, but it is an ergodic system. And this has sort of interesting ramifications. Again, if one goes through the Bible is otherwise known as Arnold's mathematical methods of classical mechanics. So this is a standard problem in that. And in preparation for today's tutorial, some of you might like to consider the following problem that emerges from this rather simple dynamical system. Consider the powers of 2, right? So we know that it starts off with 2, 4, 8, 16, 32, etc., etc. Okay. So a question that is posed is the leading digit. Just consider the leading digit of the successive powers of 2. Right? Does 7 ever appear? And I mean, you can just go on 32, 64, 128, etc. So the leading digit over here, next is 6, and then is 1, and then is 2, and then is 5, and so on and so forth. So the question that is posed is, does 7 ever appear? Or, big one? I'm multiplying. These are just powers of 2. I'm not squaring them. Yeah. Right. I mean, this is, if you like, a problem in experimental mathematics, right? But it's the kind of question which you sort of, it depends on ergodic theory, all right? And there are remarkably few systems that you can actually prove to be ergodic. Apart from trivial examples like this, which is the circle, this is not quite enough for statistical mechanics because you require things to be mixing as well. Yeah? Irrational. If alpha is rational, you just get a finite set of points. It's not going to be ergodic, right? So, big one. But the rationals are measure zero, right? So for typical alpha, i.e. ergodic, irrational alpha, it's going to be ergodic. Right? Okay, so but this afternoon we'll have a tutorial, and I will come up with a problem set, so which will include this. Is there a common mailing that I can give? If I send it to you, you'll share it with everybody. I'll try to have it done by midday so that you all can have a few hours to look at it. Okay. I like these. Yes, it does. Okay, it does, but it's an interesting problem. But one. It does occur, but it takes an incredibly large power of 2, like 45 or 40. Of course, yeah. It depends on the irrationality of alpha.
No, the 2 to the power n.
Yeah.
The leading digit can be 7.
Oh, the leading digit can be 7, and.
But you just do it empirically, or you can prove it?
No, you can prove it. Yeah. No, empirically, of course, if you just sit with a calculator and just keep on mindlessly pressing multiply by 2, you will get somewhere. If anyone is having a tired wrist right now, you've done it 42 times, of some number in the 40s. All right? Yeah, it depends actually on the irrationality of the logarithm of 2. In base 10. Okay. All right, so we are interested in systems which satisfy the ergodic hypothesis. We'd like to believe in things like equipartition. You'd like to believe in a lot of, a lot of the things that are taken for granted. Boltzmann's hypothesis of molecular chaos and so on and so forth. You'd like to be able to at least show some systems where this is true. Now this actually was, some of you may have heard, was the first set of problems that was tackled on numerical computers were related precisely to questions of statistical mechanics. I'm not going to discuss them, but there was this, you've seen Oppenheimer, I presume. Has everyone seen Oppenheimer? Yeah, all right. So one of the nice outcomes of the Manhattan Project, in addition to there being digital computers, was a collaboration between Fermi and Ulam, along with another physicist called Pasta. So there's this famous problem by Fermi, Pasta, and Ulam, where they looked at a chain of oscillators, where basically they wanted to understand, these were all, the interactions were nonlinear. So it wasn't just springs, nonlinear springs and particles, right? And so, et cetera, going up till n in one dimension. And Fermi thought that a cool problem to look at was the following, that if the interaction was not just x squared by 2 plus also, let's say, x4 by 4 or I think they had a cubic term as well, and sort of the general problem, like interaction between any pair was just not Hooke's law, but nonlinear. Then the FPU problem basically was that if I put in some energy over here, equipartition will tell us that as time goes to infinity, the energy would be completely distributed in all the modes of oscillation, right? And surprisingly, and they had actually, two aspects of surprise, that in the 50s you could do calculations that were really accurate, when one finds it difficult even today. But also, more importantly, what they found was that they put some energy over here, and the energy actually traveled through the entire system and came back. So there was a recurrence of, there was no equipartition in a long time, right? You just kept coming back and back and back, and it wasn't even as if you were recurring imperfectly so that you could expect that as t went to infinity, you'd find equal energy in all the various modes. The system the system is actually, in a funny way, very close to being integrable, right? And today it is an area of study where people look at things like solitons and breathers and whatnot in chains interacting in, through simple nonlinear laws. So it seems to require a lot more to get to the statistical limit. Most dynamical systems that we look at are really a little far from there. The discovery of dynamical chaos was something that, again, sort of led to the hope that you could have this connection between statistical mechanics and dynamics coming up. Because if you had a system which was chaotic, then it was not periodic. And perhaps because it was chaotic, it was highly unstable, and things would just, again, reach the statistical limit. There was a lot of hope that that was going to be true. And of course, that was not nearly as true as people were imagining, because chaotic systems were also, to varying degrees, not as ergodic as you wanted. You did not have the equivalence. Actually, there was a lot of order in chaos, and that led to an entire new kind of excitement about the subject, right? So, so one of the reasons why, and still the dream is not, it's not been given up. People are still looking for dynamical systems where the connection with statistical physics could be made. So one of them is the Kuramoto model, which I will discuss today. And this is related in a sense to the okay, let me just describe what the Kuramoto model. If you have an oscillator, yesterday I was discussing just the simple harmonic oscillator. So you can write it as, as some kind of a loop in the phase plane. A closed curve in the phase plane represents an oscillator, right? And this oscillator has got an amplitude and a phase, all right? So the solution for this, if I write this as x and x dot, right? So x goes as some amplitude times cosine of omega t plus theta naught, if you like. So you start over here with some initial theta naught, and you're going around a circle, right? Now, let's forget the amplitude. Describe or discuss an oscillator as just the phase, right? So x just goes as some quantity like this. So this quantity is known as the phase, and for this you can write down theta dot is just equal to omega. So you've got so the oscillator is in in the phase plane, it is a closed curve. Through a very simple transformation, one can, or in this case, for the harmonic oscillator, of course, you solve it. But for any solution, it doesn't matter. If you have a cycle, and there are some simple examples that are known. Actually, I'll always come around to circular ones. So then there is an example, which is x double dot minus mu into 1 minus x squared x dot plus x is equal to 0. So for mu is equal to 0 is the harmonic oscillator. Right? And for mu non-zero, obviously there's some damping. But if you think about it in the following sense, for mu equals 0, the solution is a cosine. Right? For mu non-zero, it is damping, but the damping comes with forcing. There's an additional term. You see, there is a mu x dot, and then there's a mu x squared x dot, and the x squared is like a cosine squared, and the x dot would be like a sine. So there is some kind of a, so this is an example of a sustained oscillator, which is not a circle. Okay, this is a famous one. It's called the Van der Pol. It's the Van der Pol oscillator, and it has an amplitude of 2, I think. I mean, this is sort of eminently examinable on Mathpedia, Wikipedia, Wolfram, etc., etc. So you look at it. And here the solution is something like so, okay? And the cool thing about this is that it is an example of a limit cycle. What that means is that if I start for small x, you see that this term is minus mu, this is positive, times x dot. So solutions will grow outwards. And for large x, this becomes negative. So the solutions come inwards. So in between somewhere, there is a limit cycle. Right? And limit cycle oscillations are very common in nature. One of the first applications of the Van der Pol oscillator was to the beating of the heart, right? Because our hearts are not exactly periodic. I mean, they are periodic, but they are not simple harmonic, right? So there is and what happens is that you can, if you excite the heart, after a while you come down and come back to the limit cycle. And if you're very, if you're very cool, you can, when you, this is an example of homeostasis. You just come back to that fixed attracting limit cycle, regardless of how you perturb it. Okay. Okay. So an oscillator it's enough to describe an oscillator by its phase variable, all right? And clearly, if I've got n of them, I've got n such equations like so. And what Kuramoto did was to study the following example. Okay, so you've got n oscillators, and they're all coupled to each other through this rather simple form. And in the, where all these variables are small, if all these differences are small, this is just a very it's almost a linear coupling, right? So this was a model that was invented, if you like, by Winfrey and Kuramoto. Right? And and this has played a sort of an important role in bridging dynamics and statistical mechanics. Because I can now go to the n going to infinity limit, if I have an infinite number of oscillators, see there's only a single variable for each oscillator, which is theta. And theta, by this definition, just lives on 0 to 2 pi. So that's quite enough, right? So we can talk in terms of, okay, so what are the interesting things in such a problem? One thing which is interesting in this problem is, what are the omegas? Okay, if all the omegas are equal, all right, so you can talk about the distribution of omegas, all right? So Kuromoto considered, and I should also warn you that this is a field which is highly active on both sides, both from the StatMech point of view as well as from the dynamical systems point of view. You heard about networks last week, so you could take Kuromotos on a network or on various kinds of networks. And instead of just having an equal coupling to all of them, you could put a coupling depending on I and j, which are the two. Okay, yeah.
So I think there's a minus sign in front of the sign.
If it's theta I minus j or j minus I.
I think it's j minus I.
Yeah, it is usually j minus I.
Okay. Thanks.
I mean, to be this is the more general model to consider, theta I minus theta j plus psi, which is known as the Kuromoto-Sakaguchi equation. All these are important. We'll just have a look and see how some of these at least are discussed, okay? I mean, I'm more alluding to the form of the interaction. The sign itself will depend on how you take, so the minus sign can be taken into k if you like. It's not that important right now. Okay, so this is a model which has been studied quite extensively because it applies to a whole variety of systems, or it is presumed to apply to a lot of systems. Including things like these Firefly models that I talked about yesterday, and a whole lot of stuff. And actually also the case of the metronomes. So the metronome is an inverted pendulum, right? It's an inverted pendulum with a point of contact over here. There's a bob of mass m over there, and it is oscillating against the vertical. Now, you saw a picture of the I don't want to sort of yank it down to show the metronomes again, but you saw that, if you just leave a single metronome undisturbed, it will just oscillate from left to right at some angle theta naught, right? And at a particular frequency which can be adjusted. And it's adjusted by sliding this bob up and down, because that changes the effective length of the metronome. And since it is used by musicians, it's very important for keeping time. And Western classical music, which tends to use this a lot, has tempos or times that go from something like 40 hertz to 200 hertz. So things can be very fast, or the tempo can be very fast or very slow. We don't use metronomes in Indian classical music. Otherwise, I tell you, it will be like dhrut and vilamb and so on and so forth. The equivalent language doesn't actually exist over here. So you can just adjust the frequency of oscillation by moving the bob up and down. Now, the equation of motion for a single metronome is something like this, and part of this is just okay, so this is just the equation for a single pendulum, all right? Now, this is sort of, one can argue this is the moment of inertia, that's the center of mass of this pendulum with respect to the point of pivoting. That's G, that's the mass of the bob. Right? Some of this does not really merit too much discussion, except to say what is the origin of these various things. Then there is damping that comes. Okay, this is a phenomenological damping which has been put because it multiplies the theta dot, and you can recognize immediately that's the van der Pol term. When theta is smaller than theta naught, it sort of excites the system. When theta is bigger than theta naught, it damps the system down, and you come to some limit cycle where theta over theta naught is equal to 1 in the absence of any other kinds of forces, right? And then there is, because I'm putting this on the base, the motion of the base is, okay, so the inertial force that comes from the base is just mx double dot times cosine of theta divided by I times r center of mass. I may forget this center of mass. That's equal to 0. Okay, so this is just, it's a phenomenological equation. It's not, and I've just taken some leading terms over here. Your basic pendulum, your basic damping, your coupling to the motion of the platform on which you are positioned. Right?
So the damping also comes from the coupling. It's not the air damping.
This is just pure, no, this is the coupling.
But it's not air damping because you have just square minus 1. So it must be from also.
It's from the coupling, from the way in which the metronome is constructed, and so on and so forth. I should tell you, I'll give you the reference to, the discussion papers. This is from a paper by Pantaleon. It's an experimental theoretical paper. So many of these are taken from experiment.
But it doesn't come from the equation you wrote yesterday.
Which one?
You wrote an equation yesterday for the two pendulums.
Yeah, it's just that this is already inverted, you see. So.
But
It's very similar. I mean, the analysis is going to be very similar. And as you said, today I'm going to show you that it's the in-phase motion that is stable, or at least I'll try to discuss the stability of the in-phase motion. Okay. Now, if I take two such metronomes, right? So I have theta 1, both of them the same mass, theta 2. Okay. Then let me write down the equation for the coupled system, and so I get d squared theta 1 by d. I'm already moving to a time which is omega tau, where omega itself is your basic oscillation frequency, which is just mgr over I. Okay. This r is the center of mass. This is like the length, if you like, the length, effective length of the pendulum, right? So d squared theta 1 by plus sine theta 1 times 1 plus delta. I'm just going to come to what delta is, plus mu into theta over theta naught squared minus 1, theta 1 dot, minus beta cosine theta 1 times sine theta 1 plus sine theta 2 double prime, where the prime indicates if you like, the double derivative with respect to the variable tau. Okay. Now, just to explain what these various symbols are, delta is just omega 1 minus omega 2 divided by omega. Omega is this creature over here. Omega 1 and omega 2 are the frequencies of the two metronomes. Right? Beta, see, beta came from the coupling with the base. The base itself, the center of mass, is just equal to total mass times x plus mx1 plus mx. Both the bobs are of the same mass, and the positions of this x sub I, this is equal to x plus some okay, so this is your x, this is your displacement a sub I plus r sine theta I. Okay, so the variable x over here refers to the motion of the base. It's a variable associated with the base. I'm going to use facts like x double dot is equal to 0. That is, I'm not adding any forces to the base of the system. I'm just letting it be by itself. With respect to some coordinate system over here, these two metronomes are displaced by a distance a sub I, okay, whatever that is. But this is a constant. They're just on some base. And then because the mass, the effective mass is somewhere over here, you need to account for the fact that this motion, x sub I, is going to be moving around. After a certain amount of messy algebra, you come down to this equation, which, I mean, since I'm mostly going to do an analysis of this, let me just this is equal to 0. Okay, so this is equation for theta 1. And there's a similar equation for theta 2, d squared theta 2 by d tau squared plus sine of theta 2 into 1 minus delta, right? This just because omega 2 comes with a negative sign over here, plus similar terms with theta 2 dot plus similar terms with theta 2. Okay. Which one? The third term? Yeah, of course, you're right. And this is just with 2 going to 1. Huh? Omega is just, it's your basic MGL divided by. For each of the individual, this omega? Yeah. This particular omega, let me live with that for a moment, okay? But I mean, it'll be some, okay, so this is the difference in the frequencies made dimensionless, okay? And the dimension, I'll get back to you on this. Because in my notes, all I have is it is MGR divided by I. Okay. Like I said, you know, the final analysis is best. It's actually, I'm not even going to worry about that because I really want only leading behaviors. Because finally, we are going to be interested in a situation where omega 1 is roughly equal to omega 2, so delta goes to 0. And we'll be worrying about that. Yeah. Okay. So given this pair of equations, our analysis, I mean, like yesterday, I was worrying about a solution where theta 1 and theta 2 or theta 1 plus theta 2. So if I call this variable delta, again, removing units, and this variable sigma, right? What I would really like is equations or differential equations that describe delta and sigma. And my aim over here is to show that delta goes to 0. In long time, I want delta to go to 0. If delta goes to 0, that means theta 1 is equal to theta 2, and we've got the so-called in-phase synchronization of these two systems. Okay. So, all right. So given an equation, or given a pair of equations like this, let me just introduce you to what the equations for delta are going to look like. They turn out to be partial of delta with respect to tau plus mu into sigma squared plus delta squared by 3 minus 1 times delta plus delta is equal to 0. What I have done is to take this equation, its partner equation, subtract the two, add the two, etc. Okay? All that has been done. And then I've expanded things out to basically leading orders in delta sigma. Okay. The algebra is messy, but not undoable. So you get one equation like this. And again, this is very similar to the equations that I had yesterday for the pendulums. See, beta over here is this term. It's coming from the coupling to the base. Okay? So as I mean, the physics remains, of course, the same, that the in-phase motion, because they are experiencing the coupling to the base equally and in the same direction always, the coupling, the so-called torque from the base, that doesn't affect the in-phase motion. It only affects the anti-phase motion. All right? So in particular, if I let beta goes to 0, then both these equations, if there is no coupling to the base at all, these are independent, then we'll see interesting solutions. Basically, we'll see that there's no synchronization in that. Anyhow, so those two equations for theta 1 and theta 2 give us the following equations for the in-phase and the out-of-phase dynamics.
So this is an expansion around theta 1 equal to theta 2 equal to 0.
Not quite yet. No, this is an expansion in small delta.
This small delta.
Yeah. All right? Not small sigma. Okay. Okay. Now, if I'm going to say that delta is actually much, much less than 1, then you can see that this equation, okay, okay, so for very small delta, let me just look at this particular equation. That goes to 0. Oh, let me just write it out over here. I get d squared sigma by d tau squared plus mu into sigma squared minus 1 d sigma by d tau plus 1 plus 2 beta sigma is equal to 0. That is, in the limit of small delta, this equation just becomes the van der Pol. Yeah? this sigma squared plus sigma becomes sigma cubed, and that's what that is, d by d tau of that. Right? And the solution for this to leading order is that sigma roughly has amplitude 2 coming from the van der Pol solution times cosine of 1 plus beta tau. 1 plus beta tau, 1 plus beta being the square root of 1 plus 2 beta. Again, some of these details are not terribly important. All I want to point out is that in the limit of small delta, the solution for sigma is actually something that is oscillating with an amplitude 2. And now I'm going to actually put it back in this equation.
So this thing does not depend on mu?
Which one?
The solution you wrote down does not have any mu?
No, it doesn't. For small mu, it always goes to that is the limit cycle behavior.
So that you had that funny curve, but
Yeah.
small mu that becomes a circle.
Yeah, when mu goes to 0, this is roughly a circle. Again, these are all leading behaviors.
What was mu in the original setup, right?
Big one?
What was mu?
Mu is the original damping. It's the damping variable, right? But the point about a limit cycle is that no matter where you start, you'll always go to a final solution which doesn't depend quite on the parameter. That requires only the zeroness of this. Yeah? Okay. The corresponding equation for delta is d squared delta by d tau squared plus, okay, now this 1 plus sigma squared. Sigma squared is this quantity over here. So this is just 4 times the cosine squared of that, right? The argument is that that kind of averages out because they are fast oscillations. And all I get is this equation, mu times d delta by d tau plus over here is just my delta is equal to 0. Namely, this is just a damped harmonic oscillator. Okay, time out. What I've done is to say that for small delta, this becomes the van der Pol equation. With the van der Pol equation, the solutions, I put them in over here. The oscillations corresponding to sigma sort of average out. They are faster. And so I'm really left with an effective equation to leading order, which looks like a damped oscillator. And the damped oscillator has solution. Delta goes as e to the minus mu tau by 2 cosine of tau plus some particular thing. Yeah?
How do you impose the long time limit on delta?
Which one?
I could not follow where you impose the long time limit.
See, delta is much, much less than 1. Right? That, no, I'm looking for solutions near theta 1, approximately theta 2. So I'm starting with frequencies that are almost the same. Right? I mean, the experiment that we showed yesterday, frequencies are very close to being equal, right? And I'm looking at solutions near theta 1 minus theta 2 is equal to 0. I can do the same analysis for theta 1 plus theta 2 approximately 0, right? And that will be another such exercise. But basically what I'm trying to show is that to leading order, the equation for sigma is a van der Pol equation, and the equation for delta is a damped harmonic oscillator. And since it is a damped harmonic oscillator, the solution just dies out, and in the long limit, delta will go to 0. namely theta 1 will be equal to theta 2.
The equations look sort of symmetrical between delta and sigma,
Except for this damping term. You see, it's just that this is coupled to the motion. I mean, the in-phase motion is uncoupled from the friction provided by the base. And it's the antiphase motion that gives you that. Okay? So yesterday we were seeing that for the suspended pendulums, that was required in order to bring the antiphase solution into sync. In this particular case, it is the in-phase solution that goes more easily into sync. But for the metronomes, one does all the analysis carefully for the experimental situations, etc. Actually, both the solutions are stable. Even for the pendulums, you can find small parameter regimes where the in-phase and the out-of-phase are independently stable. Okay? So a lot of this depends on initial conditions and so on and so forth. Okay, now the point of this exercise is, yes?
Theta 1 and theta 2, they depend on time.
Yeah, they depend on time.
How that is there? Like, can you think like delta to be much better?
See, delta is just the difference. Both the thetas are depending on time. This is a case of delta is equal to 0, even though theta 1 and theta 2 are varying.
Like, if we assume delta to be much less than
Yeah.
we are inputting like they are all the time equal.
They are more or less equal all the time, or the difference between them is.
That is what you want to prove.
I'm looking for solutions near that point. I'm looking for the case where delta is not 0 but small. And all. Okay. No.
Is this mean that if theta 1 is approximately equal to when they come close to each other, then we get in-phase condition?
No. They don't have to be close to one another. This time out. Okay, there are 2 points that one has to think about. One has to look at a solution, and then one has to look at its stability. All right? So I am asking, is there a solution where theta 1 is roughly equal to theta 2? And if I call the difference of that to be delta, I am interested in the kind of solution that will emerge where delta goes to 0. Theta 1 and theta 2 can vary wildly all over the place, but the difference between them is going to be vanishing. Yeah? So I'm going to look at this quantity and I want to see the stability. Okay? The stability of this really means that the differences between them should go to 0. Okay? In original work by Kuramoto, he actually didn't discuss the whole point of stability of these things, but this is an important point. All right? That we not only look for a solution, we are also interested in the stability of that solution. If delta is such that delta goes to 0, if the solution for delta is that delta goes to 0, see, if I start out with very different delta, I may or may not actually land up near 0. So let me just ask the thing that supposing I started very close to 0, but not exactly, will that difference grow, in which case it's unstable? Or will it shrink, in which case it's stable? All right? And here, by a very hand-waving heuristic argument, just to leading orders, all I'm saying is that one of them becomes a van der Pol, the other becomes a damped harmonic oscillator. And for the for the van der Pol, you go on to a limit cycle, so you're always oscillating. All right? For the damped harmonic oscillator, you will go to a fixed point. And that fixed point basically says that your dynamics is stable over here.
I have a question regarding last sharing. So in that movie, like at the very early, we were at this phase, but then later on, it just
Yeah.
So then again,
Yeah.
so I mean, if it were to be a fixed point, the system should not go like out of that fixed point. I mean, can we
See, we do, in the movie, we don't actually know the various solutions, you know, what was the damping, what was the whole system. Like, this is all idealized, all right? So, you're right, you're observant, because that was one of the things I wanted you to observe, that you came to something that almost sounded like it was in sync, and then it broke away from it, all right? Tomorrow when we discuss synchronization manifolds, we'll see what the problems are on the manifold, all right? But that is the case. Then the second time when it came around, delta was, see, in the first case, I would just say delta was small but not small enough. And in the second case, delta was small enough, and then it went and collapsed onto the fixed point.
Okay, so like it's really, we can't say that the first time it get to that point, it was really a stable point. But
It sort of seemed to be getting over there, and it wasn't. You see, over here, I've just kept two terms. You know, then I've thrown away all sorts of things.
Yeah.
So that's
Quite
really,
idealizing the
yeah,
system.
those are the points, really.
Right, thanks.
Yeah? Yeah?
So here and in the calculation we did yesterday, we have both damping and coupling, right? So is it true so is the anti-phase and in-phase synchronization, are they both always attractors, or like what parameter does that depend on, whether it's an attractor or not?
Okay. One important parameter in this problem is beta. Okay, so as beta goes to 0, the systems become uncoupled, so you will have no attractors there. All right? Because, I mean, that's like the simple, straightforward answer, that beta is an important parameter. Mu is related somehow to the damping. I mean, I've just written it out over here. Like, so that is, again, dependent on, so these are all part of them taken from most reasonable guesses kind of stuff. Okay, there's nothing very sacrosanct about this system. But point of the story is that finally the two solutions that you see is in phase or out of phase. Moving along, I really would like to now look at n such metronomes or n pendulums or n such systems, all right, and ask what is the behavior of n of them at any given point in time. Okay, and in something that I will cover maybe in the tutorial session, let me at least say that, you see, because some of it is just messy algebra, not that this wasn't, but eventually I'm going to be interested in n of them. And see, for each one of these oscillators, I can rewrite this oscillator as theta sub I is some amplitude A sub I, let's say, I don't know, theta naught, to just remove the, to make it dimensionless, cosine of phi plus dot, okay? So finally, I get into some kind of motion which is periodic, and this oscillators will have this kind, roughly this kind of behavior where you have an amplitude and a phase. If I have a large number of them coupled to each other, then following the kind of arguments that one has been making, so on and earlier, you find that there's an equation for the amplitude which depends, among other things, on the damping, and then you have the coupling to each other. So this is some generalized version of beta. You can divide that by n. Got my minus sign there. Okay. okay, for a pair of them, we had written down some equation that looked a little like this. And I'll do this in the tutorial in painful detail if need be. But I want to just say that because you have an oscillator like so, you write down an equation for theta dot, and that will tell you how the amplitude varies and how the phase varies. And both of these come down to equations that look something like this. This is actually a cosine coming from the derivative, and I've just added a phase over there to make everything look like a sine. And okay, so let me just tell you what I'm not proving anything over here. I'm just saying that we know that these metronomes are giving us oscillatory solutions. So if writing the oscillatory solution as an amplitude and a phase, I can go into I can go into a discussion of how the amplitudes change as a function of time and how the phases change as a function of time. And let's say I'm not bothered about how the amplitudes change because they're going to, you can see that this goes to a limit cycle. So the amplitude will just go to some number, all right? Because of this form, right? Anyway, so given the fact that the amplitudes are uninteresting, all I'm left with is a set of coupled equations for the phase. And this, if I just make a shift, I can write down this as phi I dot is just equal to omega I minus k over some new constant, k over n. J goes from 1 to n sine of phi j minus phi I minus, okay. This is essentially the Kuromoto equation. Yeah.
If we are using specific reason to take sine of phi, you can take exponential of phi.
The sign came out very naturally from the fact of the pendulum. You can take xi minus xj squared if you like. Right? I mean, the part of the motivation for doing the pendulums and the metronomes, et cetera, is to say that for these kinds of of small oscillation systems, right? Small oscillation but not linear approximation. You have these interactions which are trigonometric, right? And so you will naturally get a sine or a cosine in all these systems.
Okay, thanks.
Okay, so that is the whole idea. No, I haven't made any approximation on the amplitude of the oscillation because, I wrote down those equations for the actual pendulum.
So what do you mean by small oscillations? You said for small oscillations we have nonlinear.
No, I said that these are small oscillations. These are not full. These are not fully rotational, and it doesn't have. Those motions are not being allowed, but still, we keep the full nonlinear term. When you keep the full nonlinear term, so it's very natural to see that you get the coupling to be sines and cosines. That they come up in the coupling terms. And then, of course, I'm going to throw away this entire amplitude equation because I'm not interested in it. I'm just saying that all the amplitudes eventually go, ignoring that, they'll just go to some limit cycle where AI is equal to 2. Right?
But in that equation, if k is, very large or something, then it's possible to get, it may be possible to get revolutions as well?
Oh, yeah. It's possible to do, to adjust all the couplings and whatnot to be that way. See, finally, this, I'm just motivating it, maybe unsuccessfully, motivating it from a study of pendulums and metronomes as your typical kind of coupled system, all right? And then come to a study of this equation. As a matter of fact, I'm not even going to bother about that. And I'm going to maybe make that a plus and make, sort of the standard Kuramoto model is just that.
Sir,
Yeah.
I was just wondering about 1 over n factor.
Yeah.
Is it because of center of mass, I mean, fictitious force because of the movement of the...
Yeah. It'll eventually come to something to do with that. For the two oscillator case, I just had to, this is just a normalization factor, that's all.
But this effectively makes things very interesting, right?
Yeah.
Otherwise, so I was just wondering what is the reason?
Well, I'm just, let's see where we go with this particular system, all right? So when k is equal to 0, when things are not coupled, k, remember, is the coupling originally motivated by the coupling through the the common base movement, all right? When k is equal to 0, you have a bunch of phase oscillators that are just evolving independently. So phi I just increases linearly, omega I t plus phi naught, and they are just moving around on a circle with some arbitrary initial phase, and they've got a frequency omega, and they're just moving around, drifting around independently. Kuramoto, actually, one of the nice, he did a lot of very nice things, but one important thing that he did was to introduce an order parameter. Okay, so the Kuramoto order parameter R, it's a complex order parameter. This is R e to the I psi. This is just the summation from I going from 1 to n e to the I theta I. J going from 1 to n e to the I phi j. Yeah? Okay. So if all the phi j's are identical, and this is a time-dependent quantity, all right? Because the phi j's are functions of time, and okay, so R is a function of time, psi itself is a function of time, as is phi j. But if all the phi j's are equal, right, then this quantity just becomes n times 1 or whatever, and R goes to 1. So R going to 1 is an instance of all the phi's becoming equal to one another. And then they all, if all the phi j's are equal to psi, then you have that particular situation that all of them collapse onto a common phase, and R, which is your, the real part of your complex order parameter, that tells you that, okay, now if everything is moving together, if all the phases are identical and they're moving together, right, this is an example of synchronization. So this order parameter judges whether your system is synchronized or not by asking how far are you from R is equal to 0. Because when all these are randomly distributed on the circle, R is going to be equal to 0. Okay? So, yeah.
Either phi j's are equally spaced from each other. So phi j plus 1 is phi j plus something plus constant. Would you still call that synchronized?
No, those are phase locked or what are called splay states. There must be about a few thousand papers on variations of Kuramoto. And at least in tutorial today, we shall come up with some more, right? In the sense that you name it, people have looked at it. I have myself looked at these so-called place states because you have them on a clock. Right? And one can be interested in their stability or instability. All right. So R is equal to 0 is a completely incoherent solution. R is equal to 1 is a completely synchronized solution. All right? And as a preview of things to come, as a function of, you see, what happens is that the coupling is mediated by K. As K becomes, actually we'll see that momentarily. Now, keeping this definition of things in mind, you can rewrite this equation as phi I dot is equal to omega I plus K R sine of psi minus phi sub I. Okay? Keeping the definition of R and psi, it's not difficult to just go from that summation to this particular equation over here. All right? Okay, so this is going to be my Kuromoto model, if you like, I going from 1 to n. Okay. You can ask, what is the steady state for such a system? So you want in the steady state, you would like omega I is equal to KR sine of phi minus psi. Right? That would be a steady state. But notice that this is particular to each oscillator. And in particular, if this quantity, modulus, let's say, is bigger than 1, there is no solution. There is no stationary solution. Okay? So if the point of this is that if I have a distribution of omegas, depending on the value of k, I may or may not be able to find a stationary solution for that individual oscillator. Yeah? So what tends to happen is that if I find an oscillator that comes to some stationary point, its omega must be less than kr, right? And that will give me some solution for phi sub I. I mean, these are all related, but I'm just trying to explain what happens in such a system. You start with a bunch of oscillators that are moving with positive, negative omega, what have you. They're just drawn from some distribution. So long as these, the value of omega is less than k times r, whatever the r is in that system at that moment, you will find some stationary solution. So you will find some of these oscillators either beginning to clump together, they move around, and some of them will change direction, they will do various things. As you keep increasing k, obviously this condition is going to be met for more and more and more of the oscillators. Right? So they will go to some kind of a steady state. All right? And the attracting solution there is R goes to 1. Okay, so, all right, now I will, is there some way of showing things over here? It has to be shown over there. Okay, then let's show it over here.
You also assume that the steady state basically is not moving. Every oscillator is just fixed.
No, every oscillator has the same phi.
So you also said phi I.
In
Phi I dot to 0.
phi I dot is 0 will give us this particular phi. Yeah.
Okay. So in this case, you are assuming that phi I is not changing basically.
Phi I is not changing. I'm going to be writing distributions and stuff like that. I'm not entirely sure whether this is the same as the other phi, but let's just, if you haven't seen the Kuramoto model before, okay. Actually, that has also got to be present. You want phi minus psi to be 0. It's not that phi is 0, but that phi goes to the average phase, right? Yeah. Okay, I'm not going to show this again. Okay, so this is the Kuramoto system. I've just been writing this on the board. Okay, so the natural frequencies are drawn from some distribution G of omega. And there's a lot of work done on what kind of G of omega you want. And usually it's taken to be unimodal and symmetric. So a common example, and this is what Kuramoto started with, is the Lorentzian. All right, but you could take almost anything which is unimodal. If you have bimodal, then there are issues that come with that. And remember, you can always do an overall rotation to this entire system and not change anything at all. You know, all the phases can be just multiplied by some arbitrary factor and e to the I some number. So in many situations, we will take either omegas to be 0, centered around, you know, I mean, there are all sorts of variations that people could look at. Okay, so those are the requirements. This is your okay, so this is what I wanted you all to see. So for low coupling, what happens is that essentially all these are moving around independently, all right? And they are, you know, occasionally some of them are moving in one direction, some are moving in another direction, occasional clustering, and so on and so forth. Okay. As you increase the coupling, more and more of them start meeting up with each other and staying on the same, you know, staying around some average phase. And as you increase k even more, you find all of them are essentially moving together, keeping some, you know, so the average of the phases in that is what is called psi. All right? So I can go to even larger k, in which case you will have all of them actually collapsing onto the same phi, if you like, or the same psi. Okay. This is just taken out of YouTube, so one can look at. All right. So the interesting thing over here is the collective behavior. So if you think of these oscillators as phases on a circle, all right, the degree of coherence tells you, you know, what is, you know, if all the phases are distributed around R is equal to 0. And if all the phases are more or less together, R goes closer and closer to 1. Okay? And there is a second order phase transition. Okay, but actually a square root. The power, it increases as a square root at k sub c. And Kuramoto was able to actually calculate the value of that particular, you know, what is k sub c. It turns out to be a very simple calculation, all right, which we will do shortly. Okay, so that's all I really wanted to show in this particular thing about the Kuramoto just moving around. How do I switch that off? Because see, because the oscillator itself is now no longer an amplitude and a phase, the amplitudes are all the same, equal to 2 or something like that. It doesn't matter. The phases are what are moving around, and the degree of phase coherence is measured by psi, right? By R and psi. So psi gives you what is the average phase, and R gives you the degree of coherence, all right? And like I said, you have this with increasing k, you will find that k goes to 1. R goes to 1.
What is G of, this is for what G of,
Big one?
what G of, this is for what form of?
For all forms of G of omega, so long as they are unimodal, all right, and with positive curvature, all right? Okay.
You always, with a single frequency, what happens? It was just like delta function.
If it's a delta function, maybe it's there's some odd behavior that has been studied, but
But you need a big.
I mean, if they're delta functions, they're all coherent already to start with, right? If omegas are all the same, I mean, it comes very rapidly. You know, they're not all coherent to start with, but the behavior is like this one is, let's say, typical for Lorentzian or Gaussian or any one of those. Okay. All right. In fact, if G, given a particular G of omega, K sub C turns out to be I'm just trying to get the 2 over pi times G of 0. Okay, it basically depends on well, you can shift, okay, so G of omega is adjusted so that it is centered on 0. The average of the frequencies is 0. Okay, so if you want, you've got a distribution of the omegas, right? You've got a distribution of these various ones. So you want the, okay, let me, see from this equation over here, you can see it's a straightforward step to add a little noise and go to a Fokker-Planck equation, right? For, not for the phase, but for the distribution. Okay, so you want to know what is the single oscillator distribution or single oscillator density, which I'll call rho. And this depends on the oscillator angle, the frequency, and it's a time, right? So one way of analyzing the system is to ask that in the continuum limit, when n goes to infinity, instead of talking about the phi's and the omegas themselves, I look at the density, right? And this satisfies the equation d phi by dt from here. This is equal to, from this you can write down, this is some diffusion constant d squared rho by d phi squared, right? Plus d by d phi of this quantity over here, omega plus k r sine of psi minus phi times rho. The Kuramoto model as originally written had no noise in it, so this will just go to this linear equation without the diffusion term. Okay? So for the moment we are just interested, see this is like a velocity. right? Because the right-hand side over here is just like a velocity. So this is the Fokker-Planck equation, and we're going to be interested in solutions of this Fokker-Planck equation in the limit of d going to zero, so zero noise. Yeah, but this is continuous now. This is on the, now phi's range from minus pi to plus pi. Omega goes from minus infinity to plus infinity. Actually, I'm not going to be interested in this so much. Okay. So let's just say that this is the equation I'm going to be looking at.
So basically this rho thing is the density of oscillators around that phi omega.
Yeah. All right. Let me just go a couple of steps and we'll see where we are with that. Okay. So r e to the I psi, we've already written it as summation over I e to the I phi j. And this in the continuum limit just goes to minus pi to pi e to the I phi times, if you like, 1 over n summation of j going from 1 to n delta of phi minus phi j d phi. Okay? That means I've just rewritten that thing over there, right? Okay. Which I can again take in the continuum limit now. It goes from minus pi to pi, minus infinity to infinity, e to the I phi rho of phi omega t, g of omega d phi d omega. Where I'm assuming that this is a well-behaved enough function. Yeah. It's a single particle distribution. In the phase space of this is just the circle, right? But we've already seen that phi, yeah.
The Kc you said 2 over 2 pi.
I'm going to come to that.
But the spread does not matter.
Which one? No, it doesn't matter. See, when k is big enough, it just pulls everything together, is the point.
But they keep making the variance bigger and bigger and bigger.
I mean, we'll actually see that there's a supercritical bifurcation that takes place. And the r equals 0 solution always exists, meaning that, where that doesn't, but that happens to become unstable at some point. Yeah.
When you go to this continuous limit over here,
Yeah.
you're going from a distribution of phi among the n particles to sort of a single particle distribution in the continuum, but there are you somehow assuming that in the continuum there is continuous coupling?
The coupling is always there with all the k's. What you see, finally, there is going to be a form for phi which will depend to a large extent on k. As I've said already, given any particular k, there's only a range of omega that k can manage to bring together, right? Because we want omega to be equal, omega by kr to be, to be large. Omega by kr has to be less than 1 for there to be a solution over here, right? So it turns out actually that, okay, all this is unimportant over here for today, all right. Okay, so rho has the following form. Rho of phi omega t, it has the following form. If kr, if omega over kr is bigger than 1, there is no stationary state for that particular set of thetas. And so they're just going to be moving around uniformly on the circle, except, well, they're going to be moving around with this kind of distribution, omega minus kr sine of phi minus psi. Okay, so maybe a little clumping whenever the velocity goes down, but otherwise, and when kr is less than, omega is less than kr, then you find that you have this solution, delta of phi minus psi minus sine inverse of omega by kr. See, if omega over kr is less than 1, then the solution for phi is just the sine inverse of that quantity. Yeah? Right? There are two branches depending on whether the cosine of phi is positive or negative. And I'll just say that, just remember that this is for positive cosine of phi. Abhishek? No, from...
So is the definition of rho phi omega like sum over delta phi minus phi j and also delta omega minus omega j?
No.
But so, I mean, so this step I can understand, this sum over second step. But from there to there, I mean, I don't...
From here to here?
Yeah.
No, I'm just rewriting this entire thing.
So G of omega, I would imagine also is, can be written as delta of omega minus omega.
That's right, yeah.
Okay,
Yeah, so, I mean, I've taken the rho of omega, g omega, I'm doing that integral also. That will tell you how many oscillators I have of that particular frequency, right?
Right, yeah. So the rho of phi omega t is really delta phi minus phi j and also delta omega minus omega j.
Yeah.
Sum over.
Yeah, yeah.
So it's the joint distribution in phi and
Of
omega.
phi and omega, right? Okay. Now the point is that this has got two components to it. We saw what is happening in Kuromoto. As you keep increasing the coupling, groups and groups of them clump together at some common, groups of them come together to some average value. That is this quantity, right? And there's a whole bunch of them that are moving around randomly. That is this quantity. Okay. Just very, very, very briefly, because I'm going to have to come back to it later on. R itself, this order parameter, this is going to be the integral from minus phi to pi d phi. I also need the density to be normalized, just out of interest, right? Integral from minus infinity to infinity of e to the I of theta minus, sorry, that's phi minus psi, rho of phi omega t, g of omega d omega, right? From there. Right? So now, putting in this value of the distribution function over here, I just want to dispose of this particular integral because g is, see, that integral is going to have over here g of omega d omega divided by omega plus some quantity, right? And that is symmetric. G of omega is equal to minus g of minus omega. It's symmetric around 0. So that second half of that integral doesn't exist, right? So all I'm really going to be bothered about is to looking at the coherent part of it. All this averages out to 0, right? And so this turns out, and I'm going to come back to this, as minus pi to pi d phi minus infinity to infinity g of omega d omega e to the I phi minus psi delta of phi minus psi minus sine inverse of omega by kr, right? Okay. Which, and I will discuss this later on, is just the integral of omega less than kr, so that the ratio is less than 1, cosine of sine inverse omega by kr g of omega d omega. Okay, I'm going to stop over here, but let me just summarize what I have done. I'm going from individual oscillators to a density of oscillators. That distribution, rho of phi, has two components to it. Those that have clumped together to form that coherent set, and that has this density, it's just this delta function over here. And the others which are moving all over the place, which are over here. Not surprisingly, the contribution of these fellows to the overall average is 0, because there are as many positive as negative, etc., etc. So the only contribution to the order parameter will come from here. Okay. If you like, right? So the only contribution to the order parameter will come from this part. For this part, I'm just taking this value of phi and putting it into this equation, right? Because I've written down the complex order parameter as this quantity. So the coherence part over here, R, is just equal to e to the I phi minus psi of this. Yeah? So I'm just going to, so all I'm doing really is to take this quantity, put it over here, calculate that integral. That integral turns out to be this quantity over here. And I will just write down the solution and come back to a discussion of it later on. So R just is equal to, R is equal to KR, that comes out from this delta function over here, KR integral minus pi by 2 to pi by 2 cosine squared phi g of KR sine phi d phi. Okay, so that is the calculating all these various integrals, that just comes out to be that quantity. And as you can see, there is one obvious solution, R is equal to 0. But then there is another solution that will come out of the R is equal to 0 solution by asking that this quantity be equal to 1. Okay? Doing a Taylor expansion, I'll do this again maybe this afternoon or tomorrow. Doing a Taylor expansion for G will give you, the leading order is G of around 0, right? G of 0 plus higher order terms. That G of 0 term will give you automatically the non-trivial solution for R is equal to 0. And that actually, from here itself, you can see that the value should be that Kc is equal to 2 over pi G naught. Okay? From there.
So this is sort of accurate when G is not varying on the scale of KR. When G is flat on the scale of KR, then it's exact. But then when G goes to the delta function limit, then this Taylor expansion
There
breaks
will
down.
be problems when you go to the delta function limit. So if you've got just something which has got a negative second derivative, then you can actually calculate the higher order terms and see how K behaves at Kc. Yeah? No, but I'm just saying why only G naught is because of that leading order behavior. Every other term is going to have R in it. So when you want to set R not equal 0, technically this is called a supercritical bifurcation from 0. Yeah.
So this exact solution only works because you have all-to-all coupling, is it?
Yeah. If you don't have all-to-all coupling, then you enter the world of complex networks and stuff like that. Okay, so the point really is that here is a model which has a very well-defined one-particle limit, two-particle, n-particle limit, as well as a well-defined continuum limit. All right? And in the continuum limit, we have a phase transition from a coherent state, from an incoherent state, that is R is equal to 0, to a state with some finite value of R. And in the limit of large coupling, this will go to R is equal to 1. That's going to be an attractor of the solution. Yeah? More on this. Watch the next episode. Yeah. Yeah, go ahead. Yeah.
Trying to understand, how would you think of the response function diverging at the critical point? How to physically think of it?
Okay, this is something we can talk about a little later, but all I want to say is that R will increase as K to some power.
So, I wanted to know what sort of fluctuations are we talking about over here?
See, there are for the moment, there are no fluctuations. The fluctuations are only whatever comes from the dynamics and what is coming from the distribution of the omegas. Okay? We could put in noise and then go to the zero noise limit. Okay? And that is a very successful way of looking at these systems also. But for the moment, I just want to take it as an ordinary transition, not even a phase transition. I want to go as a transition in the coherence parameter over here from R is equal to 0 to non-zero.
Also, what universality class does this belong to? This
up for grabs. This is not the directed percolation universality class, although, there's been some, I don't know. That's the correct answer is I don't know, but I don't think that there's too much discussion of the universality class of that. Yeah? Okay. Chalo.
Okay, it's working. Should I go? Okay. Okay, so good morning, everyone. So we'll restart from where we left it. So just a quick summary of what we did. So I tried to argue why the glass transition physics is broadly interesting in terms of a statistical physics problem. Then I gave you a few, key issues with the glass transition. So I described the transition between the liquid, the supercooled liquid, and then the glass. I described the structure at the level of two-body density correlation function, pair correlation function, and structure factors. Told you there was almost nothing to see beyond the fact that it's disordered, that very dense and really homogeneous in space, and that density fluctuations were not telling much in terms of the underlying physics. Then we moved to the dynamics. I defined some kind of time correlation function, showed you how they were behaving with these two-step relaxations, particle moving quickly, being surrounded by neighbors, and then at long times, a slow, very slow relaxation. We characterize this by either the diffusion constant or relaxation time, and then we sketched the behavior of the relaxation time. And I told you this was changing by, say, 12 orders of interesting, I said something like the ratio between what's happening here and here, it's about a factor 10 to the 12. So a huge increase in the macroscopic motion of the molecules. So we left it there. I told you a few things about this law. So we said nobody really knows how this delta of t is changing, but it's changing in an interesting way, in the sense that this is not a constant and it's growing because the slope is changing. So during the lunchtime, everyone was asking, so what's the functional form of delta of t, and how do you describe the evolution of this in terms of equations? And people have been arguing about this for decades in the field of the glass transition without converging on like a good description, which may sound a bit paradoxical because we have data covering 16 or 14 orders of magnitude in some cases, and we don't know the functional form of a function that changes so fast. So that's not a usual situation in physics. You have a few decades, you have a fit, and that works, and everybody's happy. In glasses, it's different. Everybody's fighting about it. Okay? So functional form for delta of t that are extremely popular are, I will give you two just to give you like the flavor of this. So one is, say, you have a temperature dependent, which is something like this, proportional to 1 divided by t minus some t0 that remain to be fitted with the data. So that type of functional form, it has a name. I don't want to write it because I will make errors. It's called Vogel, Fulcher, Thalmann, and I don't remember about the H and the double M and N. So VFT law is a divergence at some relaxation time. So of course, this divergence of the energy scale goes into an exponential, which then explodes, of course. So it means if you see a finite relaxation time, the temperature is above T0. So what people then imagine is somewhere here, there would be something like a critical temperature where that thing truly would diverge. And that's one way to think about it, is that this huge increase of the relaxation time is like the signature of a divergence which is going to happen later if you could follow the relaxation time up to arbitrary large relaxation time. So behind this, there is the idea of a phase transition somewhere. But of course, when you do the measurement, you cannot really approach arbitrarily close to T0, so you have to extrapolate its position. And of course, if this is 1 over T minus T0, this is growing, and then you can describe the deviation from RNUs. Another popular functional form would be this delta of T would be proportional to 1 over T, meaning if you have 1 over T, it's exponential of 1 over T squared. And so that law has a name. This one I know how to spell it, so I write it. It's a guy called Bessler who first proposed it, but probably other people did it. So if you think about it, again, as the temperature decreases, the delta here is going to increase as temperature goes down. You put this into the exponential, and it's going to give you a very strong increase of the relaxation time, deviating from the RNU's behavior. The difference between those two, in practice, when you fit the data, is very weak because you cannot really approach T0 enough to decide whether there is a divergence or not. But in spirit, it's very different This one has a finite temperature critical point, if you wish, and this one has nothing, just a gradual slowdown of the dynamics, which keeps going down to t equals to 0. So it's like a 0 temperature divergence, if you wish. So it's as stupid as the Arrhenius law, which is also diverging as temperature goes to 0. And it has nothing of, it doesn't have the flavor of a phase transition or something like this underlying those data. So that's like two schools of thought. Maybe there is a phase transition and everything we see is the result of the phase transition, or everything is really gradually slowing down and diverging at t equals to 0. And as I say, the data cannot really tell them apart because you can do fits and they're equally good. So these are two lines of thought. In any case, whatever, fitting function you prefer, in both cases you have, again, an apparent energy barrier which is changing as you decrease the temperature, meaning it's not like the same process that's happening and the only source of the slowing down is that you have less thermal fluctuations, which is the physics of Arrhenius. Whatever your choice, you need to describe why this apparent energy scale is changing gradually or diverging in the two cases. And this is where the interesting physics is hidden, is why is it changing at all? What's changing and what's the nature of the relaxation that makes this energy barrier grow as the temperature is decreasing? And you had a question.
What is the typical value of K0 from experiments?
Compared to what? No. So, okay. Sorry, I didn't get the question. So, usually what people do is, if you want to compare different liquids, then of course the temperature scales, they will change dramatically from one substance to the other. So usually people adopt, rescaled energy scales. So you rescale the temperature by either this one or this one, and then you express the other ones in terms of, and so it's typically, if I remember well, I think that T0, it's probably empirically again. I think there is a number, like it's a fraction of that guy, maybe 2/3, something like this. So if you have the substance at 300 K, this one would be 200. That's the order of magnitude, I think, roughly. But that's the idea, that if you want to extrapolate this, and then, I mean, it's a big mess, and so many papers have been arguing about this and that, and try to get more data there to make it more precise or kill it, and there are so many papers that have killed this one or this one that they are all dead, I think, at the end. That's okay. So that's the idea. So again, the key point is we need an energy scale that seems to be growing as the temperature decreasing. So how do you get this without invoking phase transitions? I don't know. I mean, the only cases where we understand the dynamics and we know that the relaxation time is growing in some specific way and we understand the physics. So this one we don't. The only case I know where the apparent energy scale is changing is when something like a phase transition is happening. So again, whatever your choice of a fitting function, there is no way out of, I need to think in terms of interesting many-body physics emerging, which has the flavor of a phase transition of some kind. Dynamic, non-equilibrium, statistical physics, you decide which one you prefer, but it's unavoidable. Okay, so it means the problem of the glass transition cannot be understood by thinking about two particles doing some stupid things. We need to think in terms of, what's the statistical mechanics and the emerging physical properties. So what are the emerging correlation lengths or, static or dynamical ones that are really at the root of these divergences is what I want to discuss today. Okay, so we say single particle thing, you get Arrhenius. Ordinary critical points, so you have a second order phase transition for the liquid gas, transition, or the Ising model when you cross the paramagnetic ferromagnetic, you have a critical point there. And that's the first type of phase transition you learn. So you know that there is a diverging correlation length, the fluctuations of the magnetization, for instance, or the density are growing, and attached to this, if you look at the dynamics of an object close to the critical point, you have a diverging relaxation times. It's called a critical slowing down of the dynamics. So for ordinary critical points, like the Ising model, the connection between the correlation time and the correlation length, it's a power law relation, and the connection between these involves what we call a dynamic critical exponent Z. Okay? So these critical exponents are known for a series of phase transitions, but it means if the correlation length is diverging as 1 over t minus tc to some power nu that you learn again, the connection between time and temperature would be like a power law. So tau would be diverging as the inverse of a power law to some exponent. That's never an exponential. It means all these, dynamic critical slowing down that you've learned maybe for ordinary phase transitions, they cannot explain glassy physics. So you need to do something more, okay? So Arrhenius wrong, single particle wrong, ordinary phase transitions wrong. So what's left? I left two ideas that I would like to share with you. That is critical points with disorder. Okay, so that's the key role of disorder. So if you think not of the pure Ising model, but you think of the Ising model in the presence of randomness, and that's called the random field Ising model. Okay, so you have your ferromagnetic interactions between the spins, plus on each side a random field. So that's the simplest way to introduce impurities or disorder in one of the best known models of statistical physics. So we know the behavior of that random field Ising model. It's not an easy calculation compared to the pure one. And regarding the dynamics, we know this. We know that the correlation length of the random field Ising model, when it's controlled by the disorder, it is diverging as an inverse of the power law, okay, with some exponent nu. So it's like the pure Ising model so far. But what's known is that the dynamics is very different, and you don't have a dynamic critical exponent Z. Instead, what you have is you have activated dynamics. And that's the key thing, and it's called activated scaling. And so it means the relaxation time goes as an exponential of that correlation length to some exponent c divided by t. And here you go. So you introduce this disorder. It's changing completely the nature of the critical point. It has a diverging correlation length because there is some underlying criticality. But because of the disorder, the dynamics is very different. And the disorder leads to activated dynamics with an energy scale that's controlled by the distance to the critical point.
Like that,
yeah, local single spin flip dynamics. So you do your ordinary dynamics, and the only new ingredient, and you add this random field on each side. And that's it. You follow the dynamics of that guy, and instead of diverging as a power law of this guy, is diverging as an exponential of a power law of this guy. And this psi is called something that I have forgotten. It's the dynamic exponent, I think, something like this. But that's the key. Disorder changes usually the life of statistical physics and makes things very complicated. That's one way to think about it. Some underlying criticality, diverging critical length, plus disorder. And in known cases, it's able to give you something. But then you see, you have to invoke something like a critical point. Otherwise, you cannot get that physics. So that's, I think, an interesting lesson. And the second case I would like to mention is the case of if you think of dynamics near close a first order transition, you have something like this. So close to first order transition, you call your system, nothing happens. This is the critical point, and boom, you have a discontinuity, you go to the other phase. It seems you don't have something like a diverging, it's a first order transition, you don't have criticality, you don't have diverging critical length. So how come you have interesting dynamics near first order transitions? And I think many of you know this. So imagine that, again, you have temperature, you have phase 1, and then you have phase 2. And I don't need to specify, it could be I cool water and it's 0 Celsius, and then it transforms into ice discontinuously, and that's your order parameter there. Okay, so whatever, the density, crystalline order, something, and it's discontinuous. And you know that, when you're right there before the critical point, you look at the structure and you see simple water. You don't see hints of the crystal there. So there's nothing like criticality. So how do you construct a timescale near first order transition? Anyone has an idea? You have to do some kind of dynamics. So what can you do for this? And where do you have slow things near first order transitions? What do you need to do? Okay. So let's say I cool the system very slowly. So I take this bottle of water and I slowly, gradually cool the system close. I'm approaching 0 Celsius and I want to go and it's going to transform into ice. What we know is that, again, at 0 plus epsilon temperature, I look, I see no crystal at all. It's pure liquid water, no, hints of the system. But then if I, have a protocol like this and I call, what's going to happen near first order transition, I can go a little bit beyond, and finally the system is going to transform like this. And if I hit the system and I don't go, and I don't go too fast, this is what I see like this. You've seen this before. What is it called? Hysteresis. Yes. Hysteresis means I go across the transition, but it takes some time for the system to realize it should jump to the other side. So somewhere when you see hysteresis, it means there is something slow happening. Otherwise, it would be just the same when I go up and down. Okay. So why is it slow when I cross the the first order transition? Why is it slow? What is taking so much? Why is the system having trouble going to the other phase from 1 to 2? Yes, it has to cross some kind of an energy barrier. Indeed. So how do you do when you start from 1 and then you need to end up at 2? So how do you do in practice? You transform everything at once, or you go gradually, or where do you start? How does it take place? Anyone has a name for the process? Nucleation. Nucleation means I need to start somewhere. I need to nucleate something. So indeed, and typically what you have is you nucleate a little bit of 2, and then when it started, check. It expands like this. Of course, in a big system, it could happen in different places, and you would have what we call nucleation and growth. Okay? And so what you describe with your hand, I think, is the emergence of this. It's called the nucleation, and you've done the calculation. I do the competition between, if I nucleate the phase 2, I gain energy because it's the equilibrium phase, but I have to pay some surface tension, which is like going as the surface, while the gain in energy inside is going as the volume. If you look at the competition, you see something like this as a function of the radius of this. Okay. And so at small nuclei, then the surface tension is winning, but at large size, the volume is changing, and you transform the system. And by the way, if you want to compute the rate, you need to use the Arrhenius law to express the time scale as a function of this. You say this is a fixed barrier and have to cross it. So the time is exponential of delta F. Okay, so the time for the nucleation is exponential delta F of R divided by T. So we get at least the exponential this time compared to the power law we got with the Ising model. And so why is it then sensitive to the distance to the critical point? Is because that critical nuclei that you define here, it depends sensitively on how close you are from the first order transition. So if you do a quench very deep, very quickly you go. And if you do a shallow quench, you said it takes more time there. And it's only when, the time scale of the protocol is adjusted to the time scale for nucleation that you make the transition. So it means if I'm just below the transition, the free energy gain of going to the phase 2, it's so low that, you don't go because you don't gain so much. So you take a lot of time to go. And that thing here, it's actually proportional to 1 over T minus TC, if I want to call it TC. That thing. So the critical radius is diverging if you're just below the first order transition. A lot of work just to go over things and have you talk a little bit, but what we learn from this is near first order transitions to nucleate the other phase, it takes a very long time if the thermodynamic driving force is not too big, so just there. And the time it takes to nucleate, it's exponential in a barrier that depends on the distance to the critical point. So bottom line, what can I do? I can construct again. I have a physical picture of what could happen near this first order transition. And near first order transition, I can imagine I have processes that take an exponentially large times in a quantity that depends sensitively on the distance to some critical point phase transition. So these are two examples where, activated relaxation takes place with an energy barriers that, due to the proximity of a phase transition, is changing with temperature in a sensitive manner. So these are two ways to think about how come you can get something that depends on sensitively on the temperature. In the two cases I've shown you, I had to invoke, again, the presence of a phase transition to explain the physics. Okay? So these are the two examples I wanted to give about this delta of t, just to have you think about how non-trivial it is to see this behavior while it's been known for decades that this is the case. Okay? But from a statistical physics viewpoint, it's really non-trivial to get this type of behavior. Okay, so we need to go towards, okay, fine, you need a phase transition. What phase transition do you need, and what's the nature of the phase transition? And I can tell you, if there was a clean answer to this one, it would be dead, the field. So there are proposals, ideas, mean field theories that show the types of phase transition. I'd like to go there, but again, no, 100% sure proof of everything. So I keep going with the introduction to the physics of the class transition, and I told you the structure looks boring, the dynamic looks very interesting. So structure is boring, but not everything is boring at the level of static quantities. And one thing I would like to discuss, because it's really an important quantity in the field, it's something that's called configurational entropy. So it has many names, but throughout the lectures, I'll call it just one thing, the configurational entropy. Okay, so it all started, like 70 years ago, and there was this paper that we cite all the time by an American chemist called Kautzman. So what he did at the time, he collected a large number of published data about calorimetry experiments in supercooled liquids, various substances, and he tried to organize the data in a way that made it meaningful. So the quantity that he defined, although he didn't call it that way, so I'm going to call SC the configurational entropy. And so he defined something like this. He said, I'll do measurement of the entropy of my liquid. I'll tell you in a minute how. I'll do measurement of the corresponding crystalline system, so I can crystallize and try to do calorimetric measurements in the crystal phase. And what he decided to define, for reasons that are going to be clear in a minute, is the difference between those two quantities. Okay? So I need to tell you two things. How do you measure experimentally the entropy of a system? You need to go back to thermodynamics, the starting lecture. So if you remember the connections you learned between different quantities in thermodynamics, if you measure the specific heat of a system, it's related to the derivative of the entropy. So I think ds by dt is like Cp or Cv divided by T. So if you do measurement of Cp, you divide by T, you do like a thermodynamic integration from somewhere to somewhere, and you get the entropy at the end. So you get the entropy by doing calorimetric measurements. In equilibrium, you do some integration from one state to another, and you get the entropy of the final state. So you do this for the liquid, you do this for the crystal, and then you make the difference between those two quantities. Okay? So why is it a good idea to think about the crystalline thing? So the idea that Kautzman probably had, if you read his paper, is to say, okay, we know what entropy is. It's related to the log of the number of configurations. Okay? So that's the first equation you learn when you do statistical physics. I count the number of configurations in configuration space. I take the log. That's the definition of the entropy. Okay? So what Kautzman's idea was, he said, okay, if I take the entropy of my liquid at a given temperature, I'm counting all the configurations. By contrast, if I look at the entropy of the crystal, okay, it's a bit funny because I know, and we've been there yesterday, a crystal is like this. You have just one global configuration, which is the periodic lattice. And so what are the configurations you're counting when you measure the entropy of a crystal at finite T? Are just, thermal excursions around that configurations. So what the crystal is about, it's about counting the log of the number of configurations, but at fixed structure, if you wish. Okay? You have one global structure, one global packing of your system, and just due to thermal fluctuations, you explore different microstates around that one configuration. And this entropy is telling you roughly the entropy associated to the number of microstates associated to one given structure. So in a sense, if you say, I'm counting everything, and I subtract the number that I have per structure, what I'm left if I do the difference. So that's the liquid. If I do the difference, in a sense, I'm counting the log of number of distinct structures. Okay, so when I go into the liquid, I take a look at the snapshot. It's a particular density fluctuation. It's boring, it's disordered, if you wish. But if I take another configuration, I have another disordered structure. So that difference is counting how many distinct amorphous structures do I have into the liquid, roughly. So that's the idea behind Katzmann. It's been, again, revised, discussed, made more precise, but that's the intuition. I have my packing plus thermal fluctuations, but I want to count how many distinct disordered packings I have. And this is what Katzmann wanted to do 70 years ago. So he did that for many substances and collected data for that quantity SC as a function of T. I told you we usually, to compare liquids, we need to normalize by some temperature scale. So this is what Katzmann did. He introduced some, I don't know how to call it, some reference temperature, and then he plotted that quantity versus T divided by some reference to be able to put many liquids in the same graph. By construction, that quantity then, it's 1 and it's 1 by definition. So what Katzmann found is that for many, many liquids, this is typically what you find. You find a curve that goes like this. It goes to 1, 1, of course. So it's decreasing rather steeply for all kinds of liquids. And then, of course, this is an equilibrium thermodynamic measurement. And then, you cross your TG and the system falls out of equilibrium. So whatever you were doing using, thermodynamic relations, you cannot use in the glass, which is not an equilibrium system. So the measurement stops, if you wish, there. Just as the measurement of the relaxation time was stopping, you cannot do measurements of the entropy there. So the key thing that Katzmann saw is that the steep decrease of the configurational entropy, meaning the number of distinct structures that the system can explore in configuration space, it's dramatically dropping as you decrease the temperature. And you say, well, if I'm bold enough and I try to see that thing, I'm going to define a temperature where that configurational entropy would perhaps vanish if I could explore that configuration. So it's called now TK for Katzmann temperature, if you wish. So the key fact that nobody denies is the number of distinct structures is decreasing very sharply. And so we say there is a rarefaction of amorphous structures or packings or arrangements of the spheres as you decrease to lower temperature. And perhaps, the idea that TK is a special temperature. Okay. So the underlying physical idea, again, is the fact that when you go to lower temperature, if you want to minimize the energy, you have to find very, well-adjusted packings of your spheres, very low temperature configurations. But this is becoming more and more difficult as you decrease the temperature. And maybe somewhere, there is a temperature below which you don't find any packings anymore because the number of structures goes up exponential in the system side. So there is this idea that perhaps this could be like a phase transition. Okay, and the transition would be between I have a liquid, the number of distinct packings that it can explore is really decreasing up until it's just one guy, but that one guy remains disordered. And so the transition would be between the liquid and the glass in complete equilibrium if I could really, follow and do my thermodynamic calculations down to arbitrarily low temperatures. So that's, I think I can take your question.
Couple of questions. So what? So in the experiment,
I guess what to get the two entropies, he cooled at different rates. Is that right? Like how does he get the crystal?
And then you go into a region where I'm not really an expert. I mean, he was using the crystal, so you have to study separately the liquid and the crystal. And I think he was, finding substances where the crystal could be reached, contrary to what I said yesterday. And then I think he was doing calorimetric measurements, starting from the 0 temperature crystal, increasing. So you have like a branch for the entropy coming from 0. You have a branch of entropy for the liquid coming from things, and then you make the subtraction between the two. So remember, to get the entropy, you need the thermodynamic integration. So I think for the crystal, they start from 0, and from the liquid, they start from infinity. And then they make the difference of those two independent measurements.
Okay. The other question is, so you wrote S liquid is the number of log of number of configurations, and S crystal is now what is that number of configuration? No, what is that?
So I was saying
for the given structure.
So again, you know that entropy becomes the number of microstates, whatever, the total number of them. So this one is fair. In a crystal, the macrostates are a bit complicated because you have again a frozen periodic structure, and the macrostates are, in one case you would have, the particle doing this one, so that's one microstate. Another one would be, like this, like this, like this, like this. I'm just trying to draw thermal fluctuations around the positions. And so what you're counting with the crystal is the global structure, the density pattern, if you wish. It's fixed, it's constant. And the only thing that's left are small thermal fluctuations. But of course, again, each configuration is one microstate. But you count the number of microstates at a fixed global structure.
Okay.
Okay. And so what I say, if you do the difference between the two, you count the number of how many distinct global structures you have.
Okay, but for the liquid, for a given structure, also there is fluctuations, right?
Sure, of course.
And that so there's two.
That's how you can think about it, and I'll draw it many times. You have, this is one structure, one structure, one structure, one structure, and each structure you have like thermal fluctuations around it.
Right,
That's one way to draw, microstates in configuration space. That's how to think about it, if you wish.
Okay, so the difference would one would be just because of the difference in the number of those configurations, and also
either you count this, how many of those you have, or you count everything.
Okay, but for each configuration also the entropy would be different, right? For the crystal and the disordered structure. Like if I just look at the fluctuations around the crystal, whatever frozen,
So I think the assumption that Kaufman did that people no longer do is that the fluctuations around a disordered packing or the fluctuations around an ordered one are similar.
Oh, is it? Okay.
Of course, we don't know, but people have stated, it's been 70 years, so, but that's a fair, I think, assumption. Okay.
Is there an order parameter?
Yeah, it's all in the rest, okay? I will answer your question in the rest of the lecture. So good question, very good question. Thank you. There was another.
What role would defects play in the glass strip?
What role, sorry, would?
What role would the defects play in the glass strip?
What defects?
Any kind of impurities.
Any kind of?
Some vacancies. Vacancies.
Vacancies of what? That's what I don't get.
There's a vacancy in a crystal structure. What role would that play?
Yeah, but I'm telling you, I'm not studying crystals, I'm studying disordered states of matter. So how do you define a vacancy in a disordered structure?
Is there any effect?
How do you define them? If you want to say vacancies play this role, you need to define vacancies in the first place. How do you do that if the structure of the particle is like this bunch of spheres totally disordered? Where do you see vacancies there? How do you define them? How do you think about them?
Is there any signature of those defects in the glass?
I think it's a forbidden question. You're just having the wrong starting point in mind when you ask that question. What I'm telling you is, again, you look at the liquid, there is no hole, there is no deviations from something because you don't know the ground state of the system, so you don't know excitations above the ground states. That's what I was telling you yesterday. If you want to understand excitation from something, you need to know the starting point. You need to know it perfectly. It's a periodic lattice. I remove one, it's a vacancy. I have a bunch of particles which are disordered. Which one is the vacancy? They're all the same to me. Unless you knew, the ideal, best, perfect disordered packings, and you could tell the differences because it would be a localized difference. Here you could start talking. Nobody knows that. So, of course, people have asked that question. I'm not trying to make fun of you. It's a good question. It's one way of thinking about it. And there are some experiments where maybe there is a hint that, yes, thinking in terms of rare defects could be useful, but, then what are they? Defect with respect to what? I think that's the key question. So idea of a thermodynamic phase transition comes from this entropy, and I'll try to answer to your question, but then if it's entropy and this particular entropy, the number of distinct packings that goes to 0, what's the other parameter and what is everything? And those questions are exactly understood in what I call lecture 2, which was about the mean field theory of the glass transition. It's all clear, so I could give you like the one answer to this. So the hint that something like a phase transition in the thermodynamic sense takes place at lower temperature, if I could go to lower temperatures, associated to a decrease and a sharp decrease of the configurational entropy, meaning a rarefaction of this number of amorphous packings. It's exactly realized in the mean field limit that I'm going to describe hopefully today. So that hint of Katzmann, that's why we like it so much these days. Probably many people had ideas at the time this one survived because it turned out to be the one that was true, at least in some limit that you can prove and understand analytically. Okay? So that's why we talk about Katzmann still. So if it's D, it cannot be C, it should only be E. So I would like to say something about dynamic heterogeneity, although and again, I'll try to say just the things I need to, again, for the discussion we're having about phase transition, length scales, criticality, non-trivial cooperative or collective physics as the temperature goes down. Okay? So we say if I look at one snapshot of my configurations, and this is how I draw them, so I don't pay attention to this, again, it's a dense liquid, so it means you have spheres all over the place, you have no holes, it doesn't look like defective, and it's boring. It's dense, homogeneous, and the position of that guy and the position of that guy are uncorrelated beyond like 2 sigmas. Okay, so it looks boring. Okay, that was the message of yesterday. But then we say, well, if you look at the dynamics, it's very slow, it's very complicated, and I think when we discussed, how do particles move, I said, if you want to move, your neighbors have to help you, right? So I already, I think, alluded to the idea of dynamic heterogeneity. So the question now that I would like to ask is, assume that you follow the position of each particle from some initial conditions. So these are the positions of the particle at time 0. And now I look at how really this guy is going to escape to go to the bathroom, as we said yesterday. So we said initially everybody is doing this kind of motion. It's boring. It's just the vibrations that we try to quantify, like Katzmann here. But finally, the system is going to find ways to relax. And as I said, if this guy wants to go, then this guy have to do something like this. Otherwise, there is no space to do it. So what I'm trying to say is you could follow the displacements of the particle over a certain amount of time and look at the field of displacements instead of the field of positions. So when we look at structure, in a sense, what we do is we just take the field of, and this is how we constructed the density field. So now what I'm saying is if you look at the orange arrows, then you look at the field where you have, for each particle, you have a vector which is the displacement vector between time t and time 0. And now you're left with a new field, which is not the position, but it's a field of displacement. So that field, in a sense, for each particle, you define a vector. And it knows about time as well, okay? So it's not a static quantity anymore. It knows about the dynamics. So what people have realized, and this is the idea that I was trying to sell you yesterday, is if you look at the displacement of bunch of particles here, and you look at, and you ask the question, is the displacement of particle I here, is it correlated to the particle displacement of distance r later? So let me draw another arrow. And you're asking the question, are these two arrows separated by a distance r? Are they correlated or not? And how long does it take to forget about the correlations between the displacement of particle I and the displacement of particle j? So we are asking, when we ask about dynamic heterogeneity, the same questions about the positions. Is the positions of those two particles separated by r, is it correlated? You can ask that question about the displacement field, and the answer is a yes. If we look at correlations between displacements, for the reasons I said, we see large domains of correlated motion, and that defines a correlation length that, for reasons that I will explain in a minute, we call XIV. Okay. So how do you go and measure some kind of spatial correlations for particle displacement? So I'm going to use one definition. There is 100 definition again in the literature. So we need to construct interesting fields out of these particle displacement. So I decided to choose this one, again, arbitrarily. So yesterday we looked at the quantity that we called, maybe it was a k yesterday, I forgot, k times. Okay, so I said when you sum over this quantity divided by n, that was called the self part of the intermediate scattering function in the Fourier space. Okay, so it means if I take the ensemble average of that quantity, I hope yesterday I called that quantity Fs k and t, which is the self-intermediate scattering function. So if you look at the average function, you get the time correlation functions that we were sketching yesterday. So what I want to do now, I want to look at the instantaneous value of that function for one typical particle. So I'm going to look at the fluctuations of that quantity. Okay. So I could look at delta Fi, which is Fi of t minus average, well, yes, average of Fi of t. Let me keep it like this. So just like here today, we had the density field. We constructed the average density, fluctuations of the density, and then we constructed two-point correlation functions of the fluctuations of the density. So today we say we have a field, we construct the average, we construct the fluctuations, and then we are going to look at two-point correlation functions of these fluctuations. So I can follow the same path as yesterday and construct a pair correlation function, if you wish, or structure factors, but associated to those fluctuations that are dynamical in nature. So I can go and say, and construct the structure factors. I'll just give you the definition immediately. So this one knows on time, it knows on the distance, and I'm just writing the definition. Sum over I, sum over j, different from I, delta Fi, delta F j, and then I have my delta function R. And average. So it's like a pair correlation function where you look at interparticle distances, as I was doing yesterday, but now you correlate fluctuations of the dynamics for particle I times fluctuations of the dynamic for particle j. So it's the analog of the pair correlation function, but now weighted by dynamic fluctuations. Okay, so I told you yesterday, if you plot d over r, it's boring. It has a few oscillations and it decays to 1. If you plot that function g over r on d for a certain time, it's looking a little bit like g over r, but then I'm exaggerating a little bit. It's never that clean and nice, but that's the idea. That thing goes to 1 if you normalize it, and now if you look at the envelope of that function, it decays with a non-trivial correlation lengths that depend then, of course, on the temperature and on the time scale you chose to look at the dynamics. Okay. So typically, people chose, they say we look at the typical correlation time of the system, and we look at the correlation times, how the particles have moved in space, and we look and we characterize the spatial correlations of the particle displacements over a time scale corresponding to the relaxation time of the system. Of course, people have studied the time dependence, but it's too complicated for today. So again, why am I exaggerating this? So the key finding is that if you define that XIV quantity, first of all, it's much larger than the stupid, boring, static correlation lengths that you extract from just looking at the density fluctuations. It means inhomogeneities in the dynamics are much more pronounced than the inhomogeneities in the statics, one. Okay? And two, if you look at this quantity and you follow its temperature dependence, it is growing as the temperature decreases. Okay? So that's the message I wanted to share already with you, which is a bit intuitive. When it's very dense, very difficult to move, you need to move in a collective way, and so particles need to adjust and agree to move in similar directions in order to find a new state that's not too different from the previous one. So that's the key thing, I think, that excited people so much, that after so many years, nobody had found interesting, spatial correlation lengths that were changing as the system was approaching the glass transition. And then with his idea of dynamic heterogeneities, at least you can start and play and measure, time correlation functions and discover that as you approach the glass transition, really particles have to move in a correlated manner. And that correlation length was changing appreciably, and you could measure the growth of this over a larger number of particles as you approached. So it was the hint of something like a collective for the first time, and so people got excited about dynamic heterogeneity for that reason. Sorry?
No, this inside the delta function, this Ri minus Rj, did you mean delta Ri minus delta Rj?
Yeah, so what this function is telling you in a sense is you look at, again, particle distance, you look at particles separated by a distance r. So you select pairs of particles separated by a distance r.
That's the initial distance or the final distance?
I mean,
no, in the sense this delta Fi, they only...
Yeah, you're right. I mean, I should have put the time here to make it precise. You say that's what I drew here. So you have the initial positions, you draw a vector, and then you look at spatial correlations of that vector for the initial positions. Okay, so you look at pairs of particles separated by r, and you ask how much is the fluctuations of the dynamics, how much is it correlated. Exactly. So what you would say if you had the full time dependence is a plot that changes with time, and so you could extract a time dependent length scale if you wish. And people have done this. I'm trying to simplify my story a little bit.
And for a liquid, what would this look like?
It would, again, for a liquid, good question. So for a liquid, that thing would be like this. No strong correlations between the positions and no strong correlations between the displacements itself. Okay, so uncorrelated dynamics, uncorrelated density. So what I think is interesting is that this doesn't change as you cool the system towards the glass transition, but the way you move is changing a lot. Okay, that's why I was saying if you take snapshots, you can't tell really the difference between a weakly supercooled liquid and a deeply supercooled liquid. If you look at how particles move over a time scale that's changing a lot, you can tell the difference.
Volume exclusion, and then the shells
Sorry,
of
the first part of what?
So for the liquid, right? So if you look at this correlation function, you had the volume exclusion and the shells of neighbors, right? One after another. So the same argument also goes through here. Like,
yeah, so the fact that you have oscillation reflects the underlying structure because you have, in a sense, more particles here than you have here because of the structure of the liquid. So sometimes people have tried to remove those oscillations by precisely doing what I think you are suggesting. You could try and normalize that guy by the pair correlation functions, which knows about the underlying structure, and you get rid of most of these effects if you want.
A question. So I'm slightly confused here. Having a large Xi4 would mean that the displacements are correlated.
Yes.
Right? Then that would imply that the particle can more easily get out of the cage.
How do you quantify easiness?
Tau alpha.
Yeah, so what we know is that as you decrease the temperature and you go deeper, closer to the glass transition, the two things go together. It takes more time to relax the structure of the system. So to go from one state to a completely different state takes more time. That's the tau, which is changing by orders of magnitude. And at the same time, the way the particle find another structure involves more and more particles as well. Now you're saying, is one explaining the other? Like, is it because it's slow that it's more correlated, or the opposite? I don't know. It's just your view of things. I'm just telling you, if I measure this and that, this is what I find. If you want to make causal connections between the two, your choice. I can't say. So I've used that sentence several times. Because many particles have to move in a correlated manner. And each particle, at the end of the day, just undergoes pure, stupid, uncorrelated thermal vibrations. If they want to move in a collective way, then you need to wait for an event that takes more and more time. So you could say, well, having to move in a more correlated way is explaining slow dynamics, but it's just interpretation of the data now.
Okay.
But that intuitively, that's, I think, correct. But it's interpretation. You're making causal assumptions between things,
Yeah,
which is, I'm being careful there because, in glass physics, people have measured this and that, and then they say, if I plot this as a function of that, I see this. Hence, causality, which is a dangerous game to play in that field.
Okay. Thank you.
So I had a small chapter about something else, but I'm probably going to skip it to go to finally this mean field theory of the glass transition. Otherwise, I'll never move. So maybe I can mention it at least if someone is interested, they can ask me the question in the tutorial section perhaps. So the one small chapter that I'm skipping here is a chapter about something called heterostable glaciers. So I'm skipping it, and the hint is 10, 15 years ago, a glass physicist in University of Madison, Wisconsin, called Mark Ediger, discovered that he could create new types of glasses using a different protocol to prepare glasses. Instead of slowly cooling glasses, he was doing it differently in a way that I don't explain, just to arouse your curiosity. And he discovered that those glasses behave very differently from the ordinary glasses that he was used to study before. So he got shocked because he was not, making that experiment to discover new glasses, but he could not make sense of the data he was seeing from those glasses. They looked different. And after many years of explorations of their properties, the bottom line and the summary is he was able in one afternoon to prepare decent glasses samples at temperature below the glass transition that looked in equilibrium. And it's comparatively to, I cool a bulk system very slowly across the glass transition. It's as if he had prepared sample with a time scale that was something like 10 to the 6 or 10 to the 8 times slower than ordinary cooling. So if people, spend a day cooling the system across the glass transition, his samples look like systems where you would have cooled for 10 to the 8 days and you would have reached that state of glassy state. So those systems were like equivalent to super old, like geological ages glasses, and he called them heterostable glasses, and they are fun and interesting and useful for applications. That's all I'm saying. Okay? If you want to learn about it, you can ask me in the coffee break, for instance. Okay? So I would like to skip that story, hoping I, arouse your curiosity, to go to the mean field theory I mentioned. Okay. And That sounds boring, mean field, but just to give you an idea, I think the idea that, you know, something like a phase transition again was there 70 years ago. And really, those things really started to gain momentum only at the beginning of the 1980s. So it took, you know, from about 30 years to get something like a decent idea that maybe, yes, there is a phase transition that, yes, we can start to understand. And those calculations are still going on, I think, to the 20s. Okay? And it took really many, many years to understand the nature and develop and make calculation and construct what is now becoming a very solid theory of a very solid mean field theory of the class transition. Okay, so this is where we are. So it means this is very solid, but as you'll see in a minute, it's just mean field approximations hidden somewhere. But at least in that mean field approximation, things are clear and clean and can be computed. So it's at least giving a reference theory to think about the problem in a way that goes beyond, you know, I have two particles, they do this and that, and you wave your hands and you derive empirical models for the class transition. Here you don't do this, you do, you know, really hard stat-mech calculations. So the history aside is, you know, I mentioned the paper by Katzmann 70 years ago, and of course, immediately after that, you know, theoreticians got excited about it. It took 10 years for, you know, people to come. I'm just giving you the names of the, you know, key interesting papers. So there is a paper by two guys, Gibbs and DiMarzio, 10 years later. What they do in this paper is they wave their hands, essentially, but they construct like a lattice model for a polymer glass, and so it's like, you know, a chain on the lattice, and then they argue about its statistical mechanics properties. They solve it in some approximate manner, and they say, oh yes, if we look at the entropy in that model, you know, it goes to zero, at some critical temperature that resembles the Katzmann transition. So they cooked out a model and the approximations to really get a phase transition that look like Katzmann. I would say, I hope it's a fair statement. And then they say, oh, we need to think about how, you know, such a phase transition could, you know, explain the dynamics. And so a famous paper in the field is Adam and Gibbs, so it's the same Gibbs. And in this paper, they again wave their hands a lot, and they say, oh, if we have a system which has a low configurational entropy, then we assume it's going to relax like this and that, waving hands a little bit. And so what they did is they related this to the exponential of 1 over s by a simple argument that's not so solid, but that's cool to read, I think. And they say, yes, if the entropy goes to 0, the relaxation time will also explode. And that paper is, you know, in the spirit of what I was telling you before. If I have a phase transition where this is happening, then I can create an energy scale that is diverging, and I have a diverging relaxation time. And that first appeared, you know, already 20 years after Katzmann. So it's like a prehistory of the Katzmann transition, if you wish. So more elaborate calculations. So 1984, density functional theory. So you try to express the thermodynamics of the system in terms of a density field. And for instance, your friend Chandan Dasgupta has done this type of calculations for supercooled liquids a lot. So that was started in this year, and they say if we approximate and we understand the statistical mechanics of glasses this way, we can predict a Katzmann transition, involving lots of approximations, of course. Okay. Then, I don't know, something like this. There are 3 years that are interesting here where people published a lot of paper making connections with mean field spin glasses. And solving the statistical mechanics of disordered spin systems exactly in the mean field limit. So that's like a few years after the spin glass calculations of Giorgio Parisi that you've heard about. So these people, what they did is they developed new kinds of spin glass models that had different types of phase transition compared to the Giorgio Parisi ones, which were 7 years before. And they understood that in those mean field spin glass models, you have something like a Katzmann transition. So those models looked surprisingly well connected to the physics of liquids for reasons that were not understood well at the time. I'll show you probably this. In the year 2000, some lattice glass models were invented. So a little bit in the spirit of those guys. So you go on the lattice, you simplify the problem, but still you conserve, particles, densities on the lattice. And those models with some, definitions that I hope I will have time to explain, they were showing in some mean field limit, again, a Kauzmann transition. So you have a Kauzmann transition, you have a Kauzmann transition. Again, so it was an accumulation of theoretical results coming from different perspectives, and each time these models were showing similar types of phase transition, like, you have different models, but a single universality class. It's about the same story. Repeatedly, people were finding the same thermodynamic structures, starting from, different approaches, making approximations, but, all the time you found the same types of physics. And then I go back to, and I said 20s, even though it's not really finished, just to give you the decades. And that's liquid state theory. So you really start from, interacting particles. You have Lennard-Jones particles interacting off lattice, so it's like a real liquid this time. And you have to make some approximations. And the approximation you make is that this liquid is living in space dimension D. And if you want to close the equations and find a solution, you have to take the large D limit. And in that sense, this is why I'm calling this all a mean field theory for the glass transition. You do, exact liquid state calculations for real liquids, realistic liquids, atomistic models of liquids. And to make the calculations exact, you make that approximation. And in that limit, you can do calculations exactly. I mean, as you can imagine, given the number of years it took to even start the calculation and to complete the calculation. It's not an easy one, so it looks boring to go to large dimensions. But remember, you have an off-lattice interacting many-body system. Those calculations are really heavy and not easy to follow, and took, from that guy to this year, took 70 years to arrive to a solid mean field calculation that essentially reproduces the hint of Kauzmann. But now we know in what limit exactly those liquids undergo this kind of phase transition, and we can understand and prove it. So there is a book written about this mean field 2020, I think, and you recognize at least one of the authors. So it's Parisi Urbani and Francesco Zamponi. And the title of the book, it's called Theory of Simple Glaciers. And so it's deriving statistical mechanics, mean field approaches to understand the physics of those simple glaciers. And it's very pedagogical. So at least if you want to have a hint of the calculations behind everything I'm going to say today, take a look at the book. It's very nice. Okay, so if I want to explain or give you some intuition about how mean field looks like, I can start with any of these approaches and then show you how it works in terms of the dynamics and the thermodynamics. So I'm going to choose this one because this is the one that's simplest, and it's making interesting connections between dynamics and statics. And so I go back a little bit in years, but my, I think, justification for doing this is that if I did the hard calculation, starting from the liquid, solving exactly in the limit of large D, you would find the same physics. Okay, so I'm just explaining the same physics in a case where I can at least write down a few equations for you. And so I'm going to discuss the physics of one of those mean field spin glaciers, and I will explain what it contains in terms of physical behavior. And so this one spin glass model that I'm going to show you, I chose one specific one. I think in the first papers they were using Potts spin glasses, then they went to different kinds, and then finally they realized that the ones where calculations are more transparent and easier to go to the end are the spherical p-spin models. I'm just writing you the Hamiltonian of the model. So it's a spin glass model. Instead of having pair interactions between two spins, like in the Ising model that you know, you have the p-spin interactions, or interactions between p-spin. It's a spin glass model, so you have random coupling constants for each of the p-spin that you chose. Okay. So the Ising model would be this guy is a constant, and you would have p equals to 2, and that's the Hamiltonian of the Ising model for ferromagnetic interactions. So these are the ingredients of the model. So as I said, you have these p-spin interactions that make it a bit more interesting, and interesting physics emerges for p larger or equal to 3, so that's why we don't choose the 2-spin model, which is way simpler. You have quench randomness, so you have quench disorder, so disordered interactions. So I told you if you want to see something non-trivial in that field, you need disorder anyway, so that's where the disorder. Here it's put by hand, it's in the definition of the Hamiltonian. And maybe I should specify these interactions between all p uplets of spin. So this is fully connected interactions, okay? So it means each spin interacts with everybody else. And the fully connected nature of these interactions means I'm studying a mean field model, okay? So it means there is no space, there is no geometry, there is no two-dimensional square lattice of everything. You know, everybody interacts with everybody in a fully connected manner. And this is the key ingredient to make things analytically soluble. So either you make like uncontrolled approximations in 3 dimensions, or you make exact calculations in simpler mean field models from the beginning. This one you can define in 3D, but then to solve and make progress, you have to go and say do approximations, or go to the beta lattice where you do mean field approximations. And this one you have to make an approximation instead of studying the real thing in 3 dimensions. So in all these systems, you have to make an approximation somewhere, and this is where the, in a sense, the mean field nature of the system is hidden. So typically, you're used to probably studying, you know, spins that are plus or minus 1. These are Ising spins. So I told you I'm taking a spherical version of the p-spin model. Again, the physics doesn't change so much, but the calculations, I can write down, you know, exact result for this. So we take spins that are, you know, real variable. They can take continuous values, and you have to constrain them. So there are, again, in StatMech, different ways of making that system nice. So we take the spherical version. Spherical means you impose the constraint that the sum of the spin squared is equal to n. And some of you may have studied like the spherical version of the Ising model and did mean field calculation in statistical mechanics classes. Again, this is to make things soluble and more easily soluble. So that's the spins, the connections of the J's. And the J's are random variables such that the average of J is 0. So, you know, disorder can be positive or negative. And then you draw them from Gaussian distribution, and you say that the average of the coupling constant squares, that's totally useless, but I'm just giving it to you anyway, so that the model is well defined. Okay, so the factorial P and the 2 are just convenient things. The key thing that you find is the factor of n here, which is telling you, you know, if I count the number of interactions, I need to divide things properly so that that thing becomes well defined in the thermodynamic limit. So this is a mean field model. This is the model. So does it look like hard spheres in 3 dimensions? Not at all. Does it look like a glass? Not at all. So the big discovery and surprise of the guys who were really looking at the physics of these spin glasses at the time is they solved the problem, they look at the properties, and then they said, I've seen this somewhere before, right? It's looking like the Katzmann and the liquid to glass transition, even though I thought I was studying a spin glass problem. And so that was like, I think, a really cool insight to be able to make that connection and realize that despite the fact that the model looked nothing like a real liquid, it did behave like one. in some limit, and recognizing this, I think at the time was probably an extremely good idea. Okay. So what did they find, these people, when they solved the problem? So they studied two approaches to the problem. First of all, what's the dynamics looking like? Okay. And so they asked the question, if I simulate the dynamics, I look at time correlation functions approaching, some kind of phase transition that I'm going to describe in a minute. How does the system behave? And so some of these papers are really about the dynamics of these mean field spin glass models. So to study the dynamics, you study something that looks like the Langevin dynamics that you study in the other classes, and you just write down, a Langevin equation for the spins. I just write it down and I give you the result later. So these are the forces. So the gradient of the Hamiltonian are the forces. You have, the random noise that, again, we heard about yesterday. And the only complication in the equation is that term. And that term you need to add if you want to enforce that the spins don't go anywhere. You need this to enforce the spherical constraint. So it's a Lagrange multiplier, if you wish. And it's just to enforce the spherical constraint. So you have to solve this, and you adjust mu such that this is satisfied. Okay, but it's a technical details. We don't care so much. And this guy is just the thermal noise. So it has the usual. First of all, that its average is 0, and as J times T prime would be twice the temperature delta Ij delta T minus T prime. So just thermal fluctuations, and then it's just the forces and the Hamiltonian are there. So this is the problem you need to solve. So I give you the Hamiltonian. It's complicated. It has disorder. It follows the stupid Langevin dynamics. What's the behavior of the system? So that's what these guys were able to do. And the reason why they were able to do it analytically exactly is, again, the mean field nature of the system. And the mean field nature comes from everybody is interacting with everybody in that zone. So what does it imply? It implies that if you start to write down equations for, say, spin-spin correlation functions, for ordinary system, they would involve spin-spin-spin correlation functions. Then you would have an equation for 3 spins and then for 4 spins, and it never ends because in real systems, life is complicated. If you write equations like this for mean field models, they close into themselves, and it means if you define something like a spin-spin correlation function, that's telling you how one spin is decorrelated at a later time, and you look at the average of that thing. Average means thermal average and average over the quench disorder. So it's it's not so easy to do it, but people have done it. Then you get a dynamical equation for that guy that only involves that guy itself, and so the equation is closed. I'm just writing it down just to give you a flavor of how it's looking like. Okay, so I write it down and we take a look. dt prime, how is it? C, p minus 1, p minus t prime, dc, dt prime, t prime, something like this, minus t, minus t, minus t. Okay, and we know that at t equals to 0, this is 1. So it's a first order integral differential equation. The initial condition is specified because that's the spin-spin correlation at time 0. So that's it. If I give you the initial condition, you put this into the computer and you solve for the time behavior of the correlation function. The key thing is that that's C, that's C, that's C, and that's C. So it doesn't involve 3 spin correlation functions because of the mean field nature of the system. Okay. So I'll probably speed up that part as well. I wanted to play a little bit with it. I give you the outcome of how you study this mathematically. I just skip. And I give you, say, I put this into a computer and I show you the time dependence of these things as the temperature is decreasing. And this is where I hope I'm going to convince you that it's looking interesting. I start from high temperature and I see something like this. I decrease the temperature and I start to see something that's interesting. So that system, displays like a kind of a two-step decay. If you decrease the temperature further, you find another decay like this. If you go further like this. And for that system, you keep solving the equations, and there is a temperature that arrives where the function doesn't go to 0 anymore. And if you keep solving that equation, then you find, the same thing, but with a larger plateau like this. Okay? So it means if you look at the long time limit of those correlation functions, and this is the calculations I wanted to do, if you define Q as C of t going to infinity, you find that as you decrease the temperatures like this, it's 0, and then it jumps, and then it grows like this as you. So there is a flavor of something like a discontinuity, and the temperature where this is happening, it's called the dynamical transition. So it's a temperature where the relaxation time that I could define here, okay, depends on temperature. That relaxation time goes to infinity. So in the sketch, it looks really good, and that's the reason why, again, probably these people were struck by it. If you look, you see those two-step decay. You see a very rapidly growing relaxation time, and the system becomes non-ergodic. So it means at long time here, the value of the spin is correlated somewhat with the value of the spin at time 0. So you never go far from your initial condition in the orange phase. So this is a glass. It's a non-ergodic glass. And this is a liquid with a very slow two-step relaxation. So far, so good. So the problems come when you look at, quantitatively how it's diverging.
This equation is exact.
Sorry?
This equation is exact.
This equation is exact for that specific model. So it means here you can understand everything in the context where at least maybe you don't understand the initial starting point, why that model, but at least the calculations then are straightforward and you don't make any approximation at all. Non-ergodic, So everything's fine, but then you look at the temperature dependence of this relaxation time as the system is approaching this dynamic transition at temperature Td, and what people understood is that that was diverging as T minus Td, but in a power law manner, okay?
Here, this equation is the reason why I can't see the Lagrange multiplier.
That's it.
The T has mu.
That's the one. So initially, you start with the mu, you write it down, then you make, okay. So 30 seconds. If you want to go from the Langevin equation to this two-point correlation, this dynamic equation for two-point correlation functions, there are different paths, but it means you need to do something called Martin-Jarros formalism. You need to do some kind of field theoretic approximation for this. I don't know whether you heard this. It's not an easy trick, but then you write an action and then you try to solve and understand that action. You have to make the thermal noise and the quantities are there, and you have to average this action over those two things. So it's generating many terms. Then out of this action, you derive equation for two-point correlation function and response functions. You derive those equations, then you make the assumption that the system is equilibrated, time translational invariance. You make the approximation that response and correlation functions satisfy FDT, and then you get to there. Okay, so there are many steps to get there, and at the beginning, mu is there, but then you have an equation for mu, you put it back, and that's the final result. So it's not easy to see why mu is t at the end, but the steps are, I could give you references if you want to have a look. So if I write down the full equations, I have an equation for C, an equation for R, the response function, and an equation for mu. And then I make the assumptions I'm telling you, and I can simplify everything into a single equation.
You have to make assumptions, or so it's not completely exact. There are still assumptions.
So I'm telling you this is the dynamics in the high temperature in the high temperature phase where the system is in steady state and it satisfies the laws of equilibrium. Okay. Now you go into the glass, and here you could ask yourself, okay, how do I describe the dynamics of a glass? It's supposed to be a non-equilibrium state of matter. And if you want to do this, I'm giving you the solution to these equations, suggesting that the system is no longer ergodic below TD. And so it took several years, from 87 to 93, I think, 6 years for people to understand that if I want to study the dynamics of the glass, I need to go back to the equation I was telling him about. I need to write the equation for C, for R, for mu, and I need to solve those, and it's way more complicated. And the first people who did that are Jorge Corchan and Leticia Culiondolo in that very P-spin model. So it's a well-known, famous paper in the field. It's when people have been able to start from this, make 0, 0 assumption. In the high temperature phase, you get back to this one, but in the glass phase, what you have is aging dynamics. So the dynamic that slows down and you penetrate deeper in a non-trivial way. And violations of the fluctuation dissipation theorem emerge from solving those equations I was mentioning him before. If you don't assume FDT and you solve those complete set of equations, you discover it's violated in a very interesting way that Leticia and Jorge have discussed and worked out many years ago now, 30 years, I realize. Okay? So that is it, but in the liquid, no approximations are made, but then the result of this is we don't get the exponential of something, we get a power law. So that is going to come back and hit the mean field theory very hard in the face. It means, cool, you have all this prediction, it's all exact, but it's all wrong as well. So what do you do with it? Okay? I'll probably make a very short parenthesis here and just write one name. Again, I skip it, and you can ask questions later if you wish. So I described to you the history of the sequence of papers on the size of the mean field theory of the glass transition. There is a series of papers that I haven't mentioned where a completely different set of people working on liquids, so developing liquid state theory in the 1970s, 1980s, they started to try and derive dynamic equations for intermediate scattering functions in the liquid, and they say, how do we handle this? They are never closed. It's a hierarchy of equations. It has names, BB, G, KY, whatever. And you can close them. And so people say, okay, we'll force approximation on these things, and we'll close the equations by essentially, when you have 4-point correlation functions, you say it's the product of 2 points times 2 points. And then, you break your hierarchy. And you make some approximations that you don't control. So these people have constructed a theory for the dynamics of liquids that is now known as the mode coupling theory. And if you look at the structure of the equations, they look essentially very much like those. Instead of having a C for spin-spin, you would have the intermediate scattering function, so the density 2-point correlation function I mentioned before, the FQT function, and you would have way more complicated, and you would have one equation per wave vector for the entire density field and its relaxation. But the mathematical structure and the solutions that go and emerge from that mode coupling theory, coming from the liquid, again, they match that calculation exactly. And that was, again, the genius of these people in the 1987, 89, to make that connection, to say, I recognize the thermodynamics that I'm going to describe in a minute, but the dynamics, I've seen that before. The mode coupling people have discovered it independently. And again, that's a hint that this system and the dense liquids, they sort of know each other because they have, in some limits that are controlled or uncontrolled, they have the exact same behavior. So that's my mode coupling story. I have equations, but I'm going to skip those, but I realize anyway I have 5 minutes, so I should probably take more questions and go to lunch.
So how does this tau depend on P? We also have the P spin couplings, and you said P going to 2 does not give anything.
How this what, sorry? Which quantity?
Yeah, that relation, the T minus TD
yes.
to the minus gamma.
Yes.
Does gamma depend on P? I mean, if you change P, what happens?
I'm just trying to remember. I was working on this during my PhD thesis, so I'm trying to recollect my thoughts about it. So the gamma, I think, yes, gamma. I think, yes, it depends on P as well. So it's a number, so you, okay, and it's slowly coming back. So when you solve this type of equations, I mean, you can write down generalized types of equations, and then you have all kinds of interesting behavior that I haven't mentioned. So very close to this critical temperature, you have a power law approach to the plateau with an exponent, it's called A. You have a power law departure from the plateau, it's called B, and you have a power law divergent, it's called gamma. And those three things are non-trivial numbers, and they change continuously with the details of the coupling constants that you have here. So if you write down generalized model with arbitrary lambda and mu as coupling constants, then these exponents would depend continuously on your coupling constants. But for a given model, you have an A, B, and gamma, and they are related via complicated mathematical connection. Meaning, if you start one specific model, P equals 24, you'll find one number for those things, and they are just values, arbitrary solutions of complicated equations.
So there's a way to, this is completely speculative, but so as the temperature goes down, if the effective P goes up or something, can you get more?
Yeah, but that's not the rule of the game. I'm telling you the model is defined by P equals 24. What is it doing when you decrease the temperature? Yeah. And then, so the mod coupling people, I think, have played your game. Like they said, we introduce arbitrary coupling constants, and we adjust, the value of the coupling constants to match some data, for instance. And so, from a given set of experimental measurements, time correlation functions, you play a little bit with your things, and then you can draw in coupling constant parameters the path, and they have done this a lot. Not sure what you learned, but people have explored that idea at least. No? Yes?
So this model is spherical p-spin model. It predicts that the transition to glass. So like, what is the shortcomings of the model?
What is the, sorry?
What are the shortcomings of why the model is not right? Or what are the shortcomings of the model? Like?
Well, it's a bit like I said at the beginning. You would like to describe a dense assembly of particles interacting with the Lennard-Jones potential in 3 dimensions. And I'm telling you to study that model, you are going to take spins that are real numbers constrained to be spherical with disordered interactions between everybody else. The two models at the microscopic scale, they look, super different. And I think without doing all these calculations that I'm trying to explain to you and comparing in the details and realizing that there were connections, you cannot tell if, if I give you the two Hamiltonians, they are extremely different. One has, these p-spin interactions with quench disorder. The other one is just Lennard-Jones interactions without any quench disorder. So there are so many differences between the two models that it's surprising that they look a little bit the same in some limit, first of all. And then how do you justify, why doesn't it work or why does it work? I think it's just a miracle. It's just a finding that, and perhaps if I, go back a little bit, I gave you like a list of like 5 or 6 different approaches of similar kind of problem, and they all give you the same structure for the dynamics and the thermodynamics. So what I think we like to think about is there is like a universality class of models that have similar types of phase transitions, but in the detail the Hamiltonians look very different. I mean, similarly, you are, I think, used to the idea that you study Ising spins on the lattice, or you study liquids and you study the transition between a liquid and a gas. What's the connection between those two? you look at the critical point of the liquid-gas phase separation, you look at the critical point of the Ising model, they have the same critical exponents. It's a non-trivial thing. It's called a universality class. I think without trying hard, you cannot guess. I think I cannot guess. Maybe we understand symmetries are the same, now we have all this background, but it's a bit like this. We understand that they belong to the same class, and we realize, and we have like a list of examples of models that do behave the same. Why they do so? You change the parameter p from 3 to 2, and it's all dead. You go to another universality class. So how do you explain this from microscopic, from the model? It's not clear to me, at least. Yes?
How to intuitively think of the fact that the sum over of the spins, or SIs, I mean, not a spin.
How do you, sorry?
How do you intuitively think of the fact that this sum adds up to this constant?
You mean the spherical constraint? Yes. Okay, so again, I go back to the Ising model, spin-spin interactions on the lattice. You cannot solve this in 3 dimensions. So there are 100 ways of making approximations to solve. So you probably studied 1 or 2 or 3 different types of approximation. The self-consistent thing, the beta-Pyers approximation. There are many other ways to solve the Ising model in some things. So you can take the Ising model where all the spins, again, interact with one another. And this one you can solve exactly. It's one way to do the mean field limit. And you can construct a spherical version of the Ising model where the spins are continuous variables. And the only constraint is that sum of Si squared is equal to n. You solve this, it's behaving the same. People also you put spins that are continuous, but you constrain them, in a smooth, but otherwise plus minus one thing. There are 100 ways to construct the Ising model. Why don't we care about the specific definition usually? Universality. They all go to the same universality class. So just choose the one model that's easier to solve, and you get the answer more quickly. But essentially, they all do the same.
I had another question. When you the Xi that you mentioned,
I can't see the person talking. Okay, sorry.
Yeah, when you
okay.
When you mentioned dynamic heterogeneity, the correlation length that you talked about, would it follow some sort of a Ornstein-Zernike kind of?
Yeah, so I had the chapter about this, but I went a little bit more faster about this. So I say you can define this G4 function. So I didn't explain the 4, but who cares? So you can look at correlations in real space. This is the distance between pairs of particles, and you have a special correlation function in R space. Of course, you can, like I said for yesterday, for the density, you go to the Fourier space, and you have S of k, which is almost the Fourier transform of G of R, apart from trivial prefactor. So you can play the same game for G4. You can go and devise an S4 of k and t now, which is almost the Fourier transform of G4. And then you look at the k dependence of that thing. Maybe because you're asking the question, I can sketch it very quickly. Okay, so I told you yesterday that if you look in, maybe I didn't sketch it yesterday, by the way. So if you look at density correlation functions in a liquid, you have something like this, okay? And that oscillation occurs now in Fourier space, and it's related to 2 pi divided by sigma. So remember, G of R has an oscillation that's essentially given by sigma. So when you take the Fourier transform, it's transforming into a peak there. And I told you if you go to the limit of k going to 0, it's called the compressibility, and the compressibility diverges if you have a critical point and a diverging correlation length. But for the density fluctuations in the fluid, that's very small because the fluid is nearly not compressible. So now you go to these 4-point functions that I mentioned before, and you define the function S4 of k and t, and I chose again to fix the time dependence to this. At large k values, you're probing super short distances, so you'll find the structure of the fluid essentially. So it's going to be very close to that one. So what's changing? I told you that there is this large correlation length, so it's going to show up like this. I'm slowly answering your question. And if you plot it in linear scale, what you have here is a peak developing at low k. Okay? So low k means its distance is much larger than sigma, so it's really that correlation length. And indeed, you have a peak there. So what's the functional form of a peak? And people have used what you call the Ornstein-Zernicke. So the first thing that people have fitted is that this thing would be like S4 of k going to 0 and t divided by 1 plus q psi 4 to the squared. Okay, so that's the functional form that people use to describe density fluctuations near a second order the liquid-gas phase transition, on any kind of phase transition. And so this is one way to describe this. So when Q goes to 0, you go to that very large constant here. And then when Q becomes comparable to Xi4, then you quickly goes down. So when that thing goes to 0, that defining the wave vector such that Q times psi4 is over the 1. So psi4 is 1 over this Q star here. Okay? So you take that wave vector and 1 over that wave vector as the correlation length. And of course, we understand, and we, 20 years later, people have refined that description, but that's how it started. And, as a qualitative description, it's pretty good. Thank you very much.
There's a tutorial left for practice.
Okay.
can start. Okay. Okay, so can you hear me from back? Yeah, okay. So I think we can start then. Okay, yeah. So I have this difficult task to keep you awake, like for this coming, half an hour or so. That is the most crucial time. After that, you will automatically, okay. So the plan. Can you hear me back, like properly? Okay. Okay. So the plan is, I will sort of introduce a general concept of understanding the probability distribution, spatial distributions for any kind of stochastic process under resetting. But before going there, I would like to spend like around 10 minutes or so to introduce, not really introduced, to remind ourselves what is a Poisson process, exponential random variables, all these things. Very pedagogical. Most of you guys already know about this, but let me repeat it nevertheless. Okay, so let's begin. So let me just draw this slide. So we will have like an illustration, okay, very simple illustration where let's say this is a state A and this is a state B, okay. This could be a simple lattice where two lattices from one random walker moving from here to here, or it could be just a coarse-grained state, like then I have a hopping from this state to that state, okay. It could be anything, something like that, and whenever there is a hopping, I call it an event, okay. So, and for the timing, forget about resetting, okay. Just because I have used R here, don't think that this is a resetting thing. Just imagine that there is a hopping which is taking place with a certain rate R. Okay? So if it is happening with a rate R, so in microscopic time scale delta t, right? So what is the probability that you will see the system from here to here? So that probability is R times delta t, right? And what is the probability that it stays put in state A itself? The complementary probability, just 1 minus R delta t, correct? In delta t time step, okay. So then I can ask the following question. So what is the probability that the system stays in state A, okay, up to time t. Okay, so this is the question we would like to understand. Okay, so this t is given. This is a fixed time. Okay, so then what is the probability that it stays? That is 1 minus R delta t, right? So I can discretize this small t into many numbers where this delta t is going to be 0 and n is infinite number of intervals, right? So if you do this, so then it's very obvious that you have to just multiply over 1 minus R delta t n times, right? And if you do this and then use this discretization scheme, what you should get is e to the power minus R times t, right? So the probability that the system stays back in A, this is given by exponential of minus R times t, right? Okay. So this is something which also we call survival probability. Okay. Why it is called a survival probability? Because it's called survival probability. Let me define it as Q of t. So this is also called survival probability because let's say that I don't want to go to B, right? So I want to stay as long as possible in state A. So I am surviving the state B up to some certain time t, right? So this is the reason I can also call it a survival probability. Clear? Okay. So we can also understand this survival probability, okay, by using a different type of approach. Okay, so this is something which we can call waiting time approach. Okay, so let us draw let us have that illustration again. So let's say that I am going from A to B. Now instead of calling the rate of this process with certain rate R or something like that, let us just say that I have rather a waiting time clock. Okay, so I have a clock. Okay, I will explain what is it. So let's say I have a clock, and after certain time comes out of this clock, I make a transition from here to here. Right? Clear? Okay. And this time is random, so this will have a distribution. Okay. And this is there is something, a notation I would like to introduce, because this is a notation which I am going to use in the next four lectures. So first let me introduce the distribution for this waiting time, which is F subscript R, and this is the running time. Okay. And the way I introduce this random variable, so this is a mathematician's way of introducing distribution for a random variable. So if you define something like f(x, y), something like this, okay, so the notation goes as the follows. So this is the random variable which you are looking at, okay, and the distribution for this random variable is given by this, okay, where y is the running variable. So this essentially means the probability that this random variable takes certain value y. Okay, so this is a notation we are going to use. Okay, and how this should be normalized? If I have to normalize it, this is the variable, right? So I have to integrate over all possible y's, right? So the reason why we put x is that we can use the same function f for many different random variables. Okay, so let's say that instead of x, I would be talking about some time. Okay, so I can still use the same function. Okay, it will have a different form, but I can use the same probability just because I have used a t, okay, which would mean that this is a different function. Okay, it will be very clear when we do examples, etc. and all. Okay, it's just I wanted to introduce the notation, and as I said, the normalization will be something like this. Okay, depending on what kind of normalization you need to do. Okay, so instead of giving you a rate, I have given now you a waiting time, and I'm saying that every time there is a set R1, R2, something like this, right? Keeps on going. Then you make the jump. You wait for some time, not with the probability, but rather with a given certain time. A random time appears, R1, and then you make the jump. Then next time, like next particle is at the line, so again you wait for another R2 time, and then make a jump. Right? Okay. So now what is the survival probability? So in the sense, what is the probability again that the system stays in state A up to time t? Okay. So this is something which I want to calculate in terms of f, this distribution, the waiting time distribution. Okay. So this Q of t is given by probability that this random variable has to be greater than small t. Okay, I want all of you guys to understand this particular expression. Okay, so what does it mean? It essentially means whatever random variable is being generated from this clock, right? All of these random variables, okay, they are identical, IID variables, but all of them have to be greater than this given time, right? Only then the system stays back in A, right? Otherwise it would have made a jump. Clear? Yes? So this is the way I can define the survival probability, that the system stays in A. Once I have defined this one, now I can easily write this guy in terms of the distribution function. Yeah. So what was the survival probability? What is the way I define the survival probability? I said the probability that the system stays in A up to time t, right? So this important factor was there is a given time up to which I want to survive. In the sense, I don't want to make a transition, right? So here I have introduced the concept of waiting time, after which I make a certain jump for sure, right? So now this clock is giving me, like statistically many IID random variables, right, in time. So if I have to stay in A, I have to make sure that all these random variables, the magnitude of these random variables have to be strictly greater than this time scale. Only then I am guaranteed to stay back in A. Clear? Good. So how do I formally write this one? Now what I'm going to write is sort of a formal definition in terms of FRT. So this is, because I know the distribution, so I can write in the following way. So what is the distribution of R, which is given by this one, right? And it is actually, it has to be greater than T, right? So then it has to be, the lower bound has to be T. Then this is a positive number, so it goes all the way to infinity, right? Then I write if R d tau. Clear? So this will be my probability that all the random variables R is bounded, is at least greater than T. This is my survival probability. Okay? So now in this case, we had taken a rate process, right? So a rate process in this problem, we'll just erase this part now. So in this case, it's just R times e to the power minus RT, correct? If this is the case, I put it here, and what I get is what we got there, correct? Okay. So we looked into a general, just a simple Poisson process where something is happening with a rate R, and we calculated something called a survival probability. Okay. And we can also propose an orthogonal approach, which is given in terms of the waiting time, and from there we can again calculate the survival probability. Okay. But this problem is, this approach is slightly more powerful. Why? Because I need not give the exact expression for FRT, okay, to get the survival probability. Okay. Because this could, in principle, can come from general arbitrary time distribution. And for that, I have to calculate, I will be able to calculate Q of T. Right? Okay. And then there is finally, okay, question, okay. And finally there is, I can actually use this relation, okay, and sort of like write F in terms of Q of T. Okay. How do I do it? I can just take a derivative with respect to T, right? So this is the lower limit, so there is a negative which comes out. So then what we get is something like FRT okay. So this is my survival probability, and negative derivative of that, the change, the way it changes, the survival probability changes, the negative of that, okay, is basically the waiting time. Okay. And waiting time for what? For some event to take place. Okay. In other words, sometimes you will see that this is also, because this event is taking place for the first time, we can also call it a first passage time probability distribution. Okay. But this is a very general ideology. Okay. And then finally, I would like to just mention, now this was the question we asked, right? So now we can ask the following question. Given time t, right? Okay. So now let's say that I am waiting till time t, then there is, once in a while there are some jumps, right? So the number of jumps basically will fluctuate, right? So what is the statistics of that numbers, okay? And this is something which we call Poisson distribution, okay? And how can you calculate it? It's very simple. In delta time t, let's say this is in delta time t, this is the number, like for jumps. So this is 1, but this happens with probability r times delta t, right? And otherwise it is 0. Okay. So now you can do the same game, like write this t is equal to n times delta t and calculate the average. If you do that, you will see that this is given r times capital T. Okay, now let me just write. So this is a given time t. Okay, and the distribution of this is the mean, and the distribution is given in terms of the Poisson distribution. Okay, so the probability distribution up to some given time t. Okay, so this is given by and I think many of you guys already know what is the Poisson process and all these things. So this was sort of like a 10 minutes of recapitulation of what you guys already know. Okay, but moving forward, this will be useful, especially all these notations and all. Okay, now let us get back to resetting. Is there are there any doubts over here? Okay, good. Okay, so what we did yesterday is that we computed the probability distribution, right, for the position of the particle under resetting, but it was particular for a diffusive system, right? So we wrote a diffusion kind of process, okay, under Poissonian resetting, and wrote an effective master equation which we solved in the steady state and all. The question is, can we write some general equation? Okay, can we develop a general formalism for arbitrary stochastic process under resetting? Okay, this will be the goal of this, like next 30 minutes or so. Okay, to do that, let us again like draw a stochastic process under resetting. So let's say x of t versus t, and so this is x naught so I have some underlying process. I'm not really mentioning what is this underlying process. It could be diffusion or it could be something else. Okay, it would be more complex process. I'm not really pressing anything. And then the process continues, right? And let's say that it keeps on going. Okay, and this is position at time t, and this will be a random number, right? X at time t, correct? And then we are interested in probability distribution P r x t given I started at x naught in the presence of resetting at x r. Okay, this is something which I would like to write, and all these resetting these are Poissonian process. It has happened with rate r. Okay, so while we do this, the particular one thing that we notice, it seems that there is this concept of renewal process, which let me introduce to you. We note that these intervals, okay, because the process is starting here, and again, you know, like it is being reset here, and then again it will start here, it will reset here. So these intervals are statistically identical. Okay, so this is the reason we call the process is being renewed. Okay, so if the process is being renewed, so maybe we don't need to even look into the entire trajectory and just look into the final resetting point when we are at the last resetting. Okay, so let's say that this is the last time we had a resetting, and after that the system underwent the underlying process, okay, and arrived at position x at time t. Okay, so the new thing which I introduced is this last resetting time, right? Okay. Now, I want to calculate the probability distribution for this process under resetting, right? Now, there can be many trajectories which will give rise to this, process, contribute to this propagator, right? But there will be many trajectories, okay. And in particular, there will be also trajectories which actually have started from here, okay, and maybe reached here, okay. So this is a special trajectory, okay, which didn't undergo any resetting events. This is also statistically possible, right? So this is also possible, but this happens with certain probability, right? So there are two types of trajectory. So I have two contribution. So PR1 and then PR2, okay? So PR1, so let me throw this, we don't need this anymore, okay. So PR1 basically is the contribution from the trajectories which didn't undergo any resetting event, right? So what is the probability that you didn't have any resetting event or any event? So this is something which we wrote something like this, right? Check your note, right? Something like that we wrote, correct? And also this should be multiplied by the propagator itself, right? And what is the propagator? The propagator is for the underlying process. Do you remember what was the underlying process? The underlying process was the process without the resetting, right? And let me just recap what it was. So the R is equal to 0 case, we used this notation for this, okay? And there is no XR because the underlying is for the underlying process, right? So then what we need to do, we just need to multiply this with the underlying process, propagator of the underlying process. Is this clear? So this is the probability that it didn't undergo any resetting times the propagator using which the particle came, starting from 0. Now you note that this expression doesn't really assume anything about the resetting and waiting time, okay? What is the choice of the waiting time I am taking, and also what is the particular underlying process I have taken, okay? Now, because we want to do it for Poissonian resetting, already we have computed this. This is e to the power minus RT times P xt x naught. Okay, so this is my one contribution, which is PR1. And now this PR2 basically are the swarm of trajectories which have seen multiple resettings, correct? Okay. So this is the one which we want to kind of calculate. And now to do that, is there any question? No, okay. So as I sort of pointed out that we would like to take a look into the last resetting epoch, right? This was my last resetting epoch, okay. So what are the components we need actually to calculate this probability, this propagator, right? We need the following components. So what is the probability that the process went from time TL till time T, okay, without any resetting event, right? Because this last part didn't undergo any resetting event, right? This is the way I introduced this last resetting event, last resetting time, right? So this should have a contribution e to the power minus R times, if this is more useful, let's say, to start with. What is this interval? This interval is T minus tau L, right? So this has to be greater than T minus tau L. And then this is right? Okay. Then from here to here, the process again, as I said before, it didn't undergo any resetting. So what is the way it went? Through the underlying propagator, right? And what is the underlying propagator? So this is one component. The second component is P of xt. Now this is important. And what is the starting point of the underlying process? Instead of x naught, now it is xr, right? Okay. And then the fact that you also have to mention that exactly at time TL between tau L and tau L plus d tau L, you had a resetting event, right? And the probability for that is just nothing but R times d tau L. P is from X.
So the time is it T minus?
Right. Thank you. Yes. Okay, so all these folks are sleeping essentially. Right. Yeah, you need all these components. So once you have all these components, I can now write them together, right? Now this tau L could be anywhere between 0 to time t, right? So I have to integrate it over. So this PR2 is just R times d tau L. Then I have e to the power minus R t minus tau L times P x t minus tau L given XR. So I have now both the contributions. I have PR1, then I have PR2. Yeah.
Isn't the first contribution just the d tau L is equal to 0?
Sorry?
The first term is basically when in the second term you have this probability that R is greater than t minus tau L.
Right.
So for the tau L going to 0, like which is part of my
Yeah, then
I guess
you
the
don't
lower
have
limit of the
you don't
integration.
have any resetting event, right?
Yeah, but so what I'm asking is, isn't the first term taken care of by the lower limit of my integral?
No. That's only in the limit, right? But in principle, this can at least accommodate one resetting event.
Okay, so the lower limit there means there is a resetting event
for guaranteed
arbitrary close to
right,
time 0.
Right. It can be, but there has to be. So now we can add them together, right? And just do a change of variable, like write t minus tau L. So this tau L should be from 0 to t. So if you can do the change of variable, you will finally get the following. You will get this after doing the change of variable. Okay. So now there are a few comments, right? So what are the these are the following comments. So you see that to get the propagator, right, in the presence of resetting, what we see is on the right hand side, what you have is only the underlying process, right? So if somebody has given you P of xt, or let's say that if you want to study a process under resetting, sometimes you will have a prior information about the underlying process, right? If you have this minimal knowledge, you can actually put this here and get the propagator. Okay. Well, in general, it will be a difficult problem, right? Because you have a finite time integral, and then usually the propagators are much more complex when you are looking at a finite time. Okay. But at least this is the first starting formula. Yeah.
Yeah, sorry, I don't. Can you explain again, like how, like for the PR2, like on the third line, how does the RDTL come into play?
So this RDTL coming because you also have to make sure that there was exactly a resetting event, right? The last resetting event that took place exactly at time between time t tau L and tau L plus d tau L.
Okay, thanks.
Right? Yeah.
For this kind of probability, we will have to, like, we can only have one or d tau L because we are considering one resetting.
No. This d tau L could be, there could be multiple events in between. This tau, yeah, because we are saying that there are multiple events and all these intervals are statistically identical. So there can be many processes, but we need not look into them. You just look at the last interval, and from there you construct the process. Okay. This is more like a. There is also something like that there is no memory being carried forward between the intervals. This is also what I mean by when I say that these are statistically identical. Okay, so we have this. So this is something which we call renewal formula. Okay. Okay, and there are, like you can do some sort of games here. So for example, let's say that we are interested in the large time limit, right? Yeah.
Shouldn't there be a minus sign when you change variables?
Where?
In front of the integral.
Where is this minus?
We change variable from the towel to t, from towel to t minus towel, right?
Yeah, so this, you figure it out. This is just change of variable. If you do it, the integration limit will change.
Yeah, okay. Yeah, makes sense.
Yeah, okay. So, let's say that if you are interested in the large time limit, right? So in the large time limit, I have t going to infinity, right? And then what I note is that this first term, okay, and this is exponentially suppressed, right? So this term actually goes away, okay? And this limit essentially becomes infinity, right? So we can just write PR correct? And also another thing you note, this is something which like being sort of stressed again and again in multiple classes. You see that when we took the steady state, we lost the information about the initial condition, right? In any finite time, there will be an information, okay? But as we took the large time limit, the information went away, right? I think this particular statement has been given many times in multiple classes. Okay, so we have this, right? So can you now see the structure of this? So you have a function, right, in time, and now you have some exponential factor multiplied with it, right? So what do you think this is? Right. So this is the Laplace distribution, right? So Laplace transform. So let me just rewrite it here. Okay, so we have so I can write in the following way, right? So P tilde x, the Laplace parameter is R, right? And now x naught. So this is the steady state. Okay, so now I would really like stop and want you guys to appreciate this formula, because you see that what is appearing on the right side is the propagator in the Laplace space. Okay, so as I mentioned before, that once you start working with some stochastic process and you want to understand the effect of resetting, you would like to have some knowledge about the underlying process. And usually it is very difficult to compute the underlying propagator in real time. Okay, but what you can actually do is you can probably calculate the propagator in Laplace space, which is much more easier to do. Okay, and then what we see that to understand the effect of resetting, at least in the steady state limit, you just need that form. Okay, so it's really like a plug and play formula, right? So you know the underlying process, and also not in real time, but in Laplace space, you just plug in over there and you get the steady state. Okay, so this is something which I wanted to mention, and maybe we can just work out the case of diffusion. Okay, so let us recall what is for the diffusion. So for 1D diffusion, right, what is P of xt, right, given x naught? This is something we know, right? Yeah. The right hand side, is it? Yeah, you're right. Yes. Thanks. So the Laplace, like the Laplace transform of this guy is just nothing but P of xs x naught is okay. This, okay. So if this is the case, right, in fact, if you remember that the way we actually solve the diffusion equation, right, is a partial differential equation. But now if you go to the Laplace space, often it becomes an ordinary differential equation. Also, that is the reason it is easier to solve the propagator in Laplace space. Okay. So you have this, now you plug in here. Once you plug in here, you got back exactly the thing which we had the previous day, right? Right, where alpha naught is square root of r by d. Yes? Okay, so this is all about the steady state, and there is one simple homework I want you guys to do. So let's say that instead of having a simple diffusion equation, let's say that I have a drift diffusion process, okay? And for a drift diffusion process, you will have a propagator which looks like this for the underlying process. Probably I should have given this also as an exercise, but this is fine. I mean, I just give this one. So this is the drift term, this mu's. Okay, and then I want you to calculate the steady state. Okay. So calculate the steady state. Okay. So what we did is we used this renewal formula, right, and got into the steady state, right, and then of course once you have the steady state, you can calculate all the moments, etc. But one thing you can do also, one step ahead, you can at least try to calculate, if not the entire propagator, but at least try to calculate the moments, okay, using this renewal formula, okay. So now to do that, let's just again play the following game. So let us take the Laplace transform on both sides of this equation. Okay, if we take Laplace transform on both sides of equation, so we have something like PR xs right. So then, what is this? Px. So I'm taking a Laplace transform of this. So I have e to the power minus st, then e to the power minus rt, p of xt, x naught. Right. So this is the action I'm taking on each one of them. Right. So then what is it? Right. So this is r plus s. Then we have starting from x naught, and what we did the last expression. So now when you multiply this one, so there is a convolution which is being waiting here, right? So if you have this, so we get r, then the convolution of this entire thing, right? And then there is a 1. So then there is r by s, then p x r plus s, but this is at xr. Okay. Right? Okay. So now if you have this, something like this, so it's very easy now to calculate the moments, right? At least in the Laplace space is very straightforward. What you can do is you can just multiply both sides by x square and repeat this process also on the right hand side. So what you will get here is x square, okay, but in Laplace space in the presence of resetting, right? And all this in terms of, let me write the exact expression. So it's not really only this one, but you can write in general x to the power n. Okay. all these things in Laplace space. This is okay. So these are like really bookkeeping calculations, like it's straightforward. You have something like this from propagator in the Laplace space, you can write this one. And the right hand side, what you have, the moments for the underlying process. So this is a renewal formula for the moments. And from this, you can calculate also the moments in real time, okay? Just by inverting it. And this is actually much more easier than the full propagator, okay? Clear? Okay. Okay, so I think at least I have tried to convince you, like how this renewal formalism essentially goes through, okay? So the essential formulas are the following. One is this one for exact time, okay, at all times. And then you have the steady state formula, which is this, and the one there, okay? This is sometimes you also call it a Laplace formula or something like that, okay? But within our community. And using that, you can also compute the moments, etc. and all. Okay, so what I would like to do now, I would like to, yeah. Yeah.
If, let's say, the second term, if there was exactly one resetting, let's say, wouldn't the term look similar?
So come again?
Let's say between 0 and total time t.
Right.
There was exactly one resetting in between.
Right, right.
And probability of such an event would have been e to the power minus r t minus tau. I mean, not having a resetting, then a resetting, and not having.
And then right.
Wouldn't that and this look very?
So this, in principle, will accommodate all the possible resetting events, right? Starting from 1. So in principle, you see this term, right? It can accommodate greater than equals to 1, right? So what you are saying also will fall into this category. This was also asked by somebody else. Okay. Okay. So maybe just keep these formulas in box. And now what we would like to do is we would like to understand. So there are two different type of trajectories, right? We discussed in the starting. So there were trajectories. And both of them contributed to the complete propagator. Some of them were undergoing resetting events, possibly more than one. And then some of them didn't undergo any resetting, right? So if I look into this process at any finite time, okay, what are the qualitative and quantitative differences I would actually see in the relaxation process, okay? When the process relaxes to the steady state, what are the qualitative and quantitative difference? So this is something we would like to understand now, okay? So to do that, let me just erase the entire board. And now, just for the sake of simplicity, let's just assume that both the initial position and the resetting position, both of them are at the origin. And the particle is undergoing, and then you can also consider just simple diffusive process, just for the sake of simplicity. And let us try to understand that how this diffusion under resetting, it relaxes to the steady state. So as I said, like let us just set x naught and xr equals to 0, okay, without loss of any generality. And let us try to again recap our renewal equation, right? So we have this renewal equation, PRXT is equal to e to the power minus RT okay, because both of them are starting from 0, so I'm not really using any subscript anything anywhere, okay? Okay, so this is large time, we see the steady state, right? So we actually ignore this term usually. Now I'm looking at the approach to the steady state. right? So I want to keep this term, okay, and do an asymptotic analysis, okay, also of this integral, okay, for the large time. So what I'm going to do is I'm going to skip these details, okay, these are basically technical details, and I'm going to give you the large time details, okay, the exact results what you get at the large time, okay. And note that I will be using for the diffusion, so we will use this x square 4d tau square root of 4 pi d tau, okay. So once I do this, I get something like this. So let me just write it down. Yeah. So let me first write it down and then I will explain. Okay, so at large time it has this asymptotic form, okay, where this I function, it characterizes the way the PDF essentially relaxes in time. Okay, and so this is that is the reason why it is sometimes called a rate function. So, and there are more technical details. Let us not get into that technical details here. So this has this following form. So alpha naught y . Okay, so this y is basically the scaled variable x by t, right? Okay, so this is the large time time asymptotic form, okay, for this guy. So what we see that the probability distribution, okay, as it relaxes to the steady state, depending on where you are, because this y is x by t, right? So then I can just write in the similar way. So like mod x should be right square root of 4 dr times t, right? So you would like to see how it is relaxing in space, right? So it seems that there is a inner core, right, where this inner core is defined when the x is between square root of 4 dr t, okay, around the origin, right, from minus to plus, right? It seems that there it has this following form, okay. Now if I expand this following form, right, so we have t and then we have I x by t, right? So then if I write this, so what it will become, so alpha naught and y is mod x by t, right? So this is just alpha mod x, right? So this is the steady state. This is the steady state we got, right? On the other hand, if you look into this guy, right, which is basically outside some spatial distance, which is also growing in time, this is very crucial. You see that this is not a fixed boundary, right? This is a boundary which is moving in time. Looking at, so basically it will depend on what time slice you are looking at, correct? With that, this boundary grows, and it grows with linearly in time. And in this case, what you see is that the expression, so I have, this is e to the power minus this, right? The next one is e to the power minus RT, something like this, okay? So you see that it seems that we have got back the same kind of expression right over here, right? So it essentially means that I have actually an inner core, okay, defined by this particular boundary, the boundary of this inner core region, okay, where the system actually has reached a steady state, okay? And just outside that region, which is again defined by this boundary, okay, the system is still evolving. Okay, that is the reason it has this time-dependent form. And now if you look into this form, you see this contribution this is something which you have seen already. This is basically these are the contribution from those trajectories which have not undergone any resetting events. So what is happening that as the system relaxes with time, right? So there are two regions. In the there is an inner region where there have been, which are coming from the trajectories which have seen multiple resetting events, and the system essentially is stabilized near the resetting position, right? That is one part, which is giving rise to this. And just outside that core, okay, there also a place where basically the system is still evolving. And this evolving region, these are essentially coming from the, are getting contributions only from those trajectories which have not seen any resetting events. And as we see that as time grows, this event essentially will be suppressed, right? So more number of resettings you will have, the system will stabilize faster. This is something also we have, I cannot really show you here, but this is something also we have seen in experiments. So if you can compare a system with less number of resetting events and more number of resetting events, you will see the systems with more number of resetting events actually stabilize faster. Okay? So this is the usual relaxation phenomena that happens, which is a bit of unusual. And just to keep this picture in mind, I would like to draw a light cone kind of picture. And this, let me do it here. And this is a picture which you can, if you can just remember, take home message. So let's say this is my time. This is the time axis, okay, over here, and this is my space. And this is my resetting position, right? Initial position, resetting position, same, right? And now I have something, right, which grows linearly in time, right? And then there is a region which is given by this for each given time, right? It's linear, so it something like this, right? And this width should come from this one, right? Goes as T. And this is this inner core, where I see the system has reached a steady state, okay? And this is this outer region where the system is still in transient phase, non-equilibrium steady state. Okay. And in principle, for simple diffusive process, this is a linear, but in principle, you could have a curve, okay? You could have a function t to the power some alpha, okay? This boundary, okay? Is this clear? So we have this boundary which is growing in time, and this the x has to be in between for the system to reach the steady state. So it's in between, right? This is the inner region. And then outside this region, right, which is when x is greater than this, right, then the system is still relaxing, right? This is the probability for that. Okay? Okay. So I think I will stop here, and for this particular part, and I just wanted to, we have tutorials today, so I will try to cover some of the things if you have questions from the previous class, and also something if you want to know from here. And there are these homeworks which I have given, right? So I'm not sure whether we will be able to cover these homeworks over here. Okay, mostly I will be clearing your doubts, etc. But if time permits, I will do some of these examples. Okay, but I want you guys to go back home and try to do these examples. Okay. Okay, so there is finally again going back to the this renewal equation. I will just end the discussion by saying the following: that we had this form, right? This PR xt x naught xr. Perhaps I have mentioned it already, but I will just repeat it one more time. You see that the reason this approach is very powerful, okay, more than actually using this Fokker-Planck equation. The Fokker-Planck equation we derived yesterday, right? What was the Fokker-Planck equation there? We had del Tp r is minus Rp plus something like this, right? And you see that when we derived this Fokker-Planck equation yesterday, right? We used actually all the properties for the diffusing process. We had to use it. right? Like for example, property of the microscopic jump, because I have to specify which process I am looking at. But when I write this formula or the Laplace formula after taking the Laplace transform, I actually do not need to specify what is P naught until I reach a position where you have given me a process and then I want to look at it. Do you see the point, what I'm trying to mention, trying to sort of like emphasize here? Okay, so this is something which should be, very clear in mind. The reason why this renewal approach is actually more powerful than individually solving Fokker-Planck equation for different process. Okay, because here I need not, when I derive this, I have not imposed any specific choice of the underlying process. So if you have, because many of you are from different arena, right? And you are probably studying different type of stochastic process of different kinds. So whatever your favorite process is, just take that, use it in here with, of course, with some sort of like understanding that you are doing it correctly, and you should get the result for the steady state or the transient process, whatever. Okay? And then there is a small homework again I want to give, that I want you guys, so this is the general solution, right, in terms of P0. Right? Now, I want you to plug in here, okay, and show that this equation satisfies this, right? It has to, right? Because this is the general equation, so this has to satisfy this. But for the diffusive process, so you, at some point of time, you have to invoke the diffusive property. And what will be the diffusive property here? What is the property of the diffusion which you have to put here? Very simple, right? You have the P0 here. So you have to just, because when you take the derivative del t, right? So this del t also will come somewhere here, right? At some point of time. So when you have this, so you just invoke del t P naught is equal to this. So together with this and this, you should be able to prove that this is actually the solution of this. Right? Okay, very well. Okay, so I think I will stop here for this, the transport properties or the spatial distributions and all these things, okay? And I will try to shift the gear and go to the first passage properties, okay? If you have any questions, maybe I can take it now. Yeah, just give me a second. Yes.
I don't know if this is very relevant, but this this form of P, it looks exactly like what we would do if we were doing large deviations. And
this is the rate function, large deviation.
So it's exact. That means for any resetting process, it can be written down in this form.
That is, it has to be with a caution, right? So if I understand whatever studies have been done, so usually we are able to write resetting a large deviation form. In fact, if I am correct, I think also there are processes for which you cannot write a large deviation form, but with resetting you can write a large division form. Okay. Okay. So obviously, when you try to write a large division function, it basically allows you to understand the relaxation a bit. Okay. But more or less, the understanding is you need to understand when it relaxes, there is an inner code and then there is an outer code. Okay. So if you understand this, that's enough. Okay. Rather is the rest is rather technicality. So this is, like we started from a short time, like any time arbitrary time process, right? So this is the reason we wrote the entire renewal equation. Okay.
Excuse me.
Yeah.
Here we have used an assumption that, not an assumption, we are saying that x naught is equal to xr.
So this x naught is equal to xr, for this one you are saying?
To derive this we did, I think so, right?
This one?
Yeah, that formula.
Yes.
We want x naught is equal to xr, otherwise we won't get this.
So well, no. If you don't have, if you have xr, right? So it will just peak at x is equal to xr, x minus xr. It will just shift, right? So you see that when your resetting happens, right? This is the origin for this case. Otherwise, you will have the same light cone, but it will be concentrated at xr.
Okay, this will ultimately be concentrating at xr.
Right, this because that is the reset. Just for the convenience, you can just take x naught xr is equal to 0.
Okay.
Yeah, please.
Right. The renewal equation, the modification of it can be written, or
Yeah, you can write the renewal equation. Of course, you can write the.
You just put a P of tau there.
So you have to put a P of tau here. You also have to know like when the statistics of the last time resetting, right? Here it is very simple. You had the last time you had it is happening with R times tau L. You will not have any terms like that, right? Rather you need to know the backward recurrence time, which is what we call backward recurrence time distribution. So what is the waiting time that you had a last resetting at tau?
Okay.
But you can explicitly write it. There is no problem writing it.
I see.
Obviously, this one is easy rather, right? This
Exactly.
one you can see it because this is the way I started, probability R greater than T.
Exactly.
So you can invoke the same kind of approach also. Yeah.
But then, of course, after that it becomes difficult because
You
no more
cannot
Laplace
you cannot do
transform.
the Laplace transform.
But
of
at least you
course.
can write it formally.
Right. Of course, you can write the formula, and also another thing is that you also have to make sure that the intervals, like they remain identical and independent. Because sometimes you have when we talk about waiting times, like power law waiting times, you might think that the intervals are also correlated.
Right.
So you cannot do that. You have to switch off everything when you reset.
Right.
Yeah.
So I'm just thinking, like, if you solve this last equation by just doing the space, like from the spectrum, then you'll get the ground state and then the first excited state.
Right.
So it would look like it has exponential decay, but then from here it's not clear that you have the same structure. I mean, the long time.
So yeah, right.
Is it a gapped spectrum or is it continuous? Is it?
I think it's a
spectrum.
Okay, so this spectrum, yeah.
Is it
right.
continuous? Gap?
No, this is.
Huh? Gapless. Then it's okay. Right. Yeah.
Okay.
I guess, but that's why you don't see as purely exponential relaxation.
I see.
Is that right? That's right.
I don't remember actually. Yeah. So we have the steady state, and after that there is. You're saying that there is no gap.
If there was a gap, it should have been just simple exponential
Simple
relaxation.
exponential,
Right?
right.
But from that form, it looks like it's quite non-trivial.
Right. Yes. Okay. Okay, so what we are going to do in the rest of the class is we are going to study first passage properties. Okay, so I'm going to explain what is it. Yeah, so basically the first passage is this is an event, okay, for any stochastic process of your choice, and let's say that this stochastic process does something specific, okay. So if you are thinking about a random walker, okay, so this stochastic process is just the position of the walker, and when this walker reaches a certain particular step or particular position in the lattice or something like that, you just call it the process has ended, okay, and this is what I would call a first passage process. And again, similarly, there can be multiple this kind of process, okay, and not related only to physics, but also you can think about chemistry when two molecules essentially meet and then they do a reaction. The first time they meet, that is also a first passage event, okay. So, and in the literature, like there are many names for this, like first passage, first exit, first encounter. There are many different kind of, like nomenclatures for this. But generically, like there is a stochastic process. It does something specific, and which ends the process is something we will call a first passage process. And the reason we call it a first passage because the first time this is happening, after which the system, basically the process is ended. Okay, so this is, and there are there are many studies and on first passage process in different kind of literature: physics, chemistry, mathematics, economics, finance, etc., etc. And one of the sort of important goal in the first passage process is to come up with different kind of strategies which can make the search process efficient. Okay? So this is some sort of a very general, broad goal of any kind of first passage process. Okay? And the idea we have for when we started thinking about, like, when the initial thoughts started regarding applying resetting to first passage properties, first passage kind of processes, was that whether you gain, there is some sort of like efficiency, okay, in the completion time by doing this resetting. Okay, this was essentially the sort of like the aim with which we started employing different kind of resetting mechanism. Okay, so before we even go there with resetting, etc., I think we need to set the stage with some basic definition, etc., for first passage, okay, which will be useful going forward, and not only for this class, or also like for you if you do something else later on. So, just for the sake of simplicity, just imagine that you have some sort of a domain, okay, and it could be in any dimension or something like that. These are not really that crucial. And let's say that this is a domain, okay, and through which this is a confining, arena, okay, and there is only one escape domain, like of some certain volume or something like that, through which the agent, the worker, the searcher can escape, okay, and once it goes out, it cannot come back, right? So let's say that I start from this position O, and then I have different trajectories. Okay, these are continuous trajectories. Okay, like in the sense like you could have diffusion or anything. It's not necessarily long jumps, but whenever it goes out, the process ends. Okay, and because the process is stochastic, the dynamics is stochastic. The time it takes to go out, that is also stochastic, right? That is also random. So then we should talk about the distribution of this quantity. Clear? Okay. Instead of having this kind of target, like on the boundary, you could have situation where the targets are actually inside the arena. So let's say that instead of having this is an exterior problem when you just go out and then never come back. But you could have some sort of an interior like problem where you have, let's say, a different type of targets here. Okay, and then you started somewhere here, and then let's say first time you hit this one, the process ends. Okay, something like that. Okay, again there is a first passage time. So this is the overall idea of first passage. Okay, well now you have a stochastic process, let's say given by x, right? So the first thing you would like to do is you would like to think about the probability distribution, right? And it is not really important at this point of time how I solve the probability, the equation for the probability distribution, etc., but more on the formalism level. Let's say that I have a stochastic process defined by some random variable x, okay, in this particular case the position, but it could be something else, okay, some random variable, and let's say that p of xt starting from some initial condition, okay, this is my probability distribution function, right? Okay, so then what is the, so because you have, let's say focus on this one, let's say that because you have an escape route, right? So if you look at this process up to some given time t, okay, and if this time is very large, there is a possibility that some of this, there will be a leakage of probabilities from here, right? Okay, so first of all, let us just close this boundary. Let us forget about that there is a boundary, okay? If we don't have a boundary, so then what is this? What is this? 1, right? There is no loss of probability, right? Okay. But now, if you just open this boundary, right? So there is this, like with time there is a leakage, right? So then what I should be thinking about, something called survival probability, which we actually defined before, right? So then this is my survival probability. Okay, so as we can see, the survival probability is actually 1 when the system is well defined, normalized, everything, right? There are no constraints. But as soon as we open a boundary, okay, which could be a, like a fixed boundary, or it could be a time dependent boundary. There could be many possibilities, right? So this becomes less than 1, right? Okay, so this is what my survival probability. And formally in words, this is the probability that the particle can be found inside this domain up to time t, right? Okay. So we need to, when we do this, right, we need to now, in the presence of the boundary, we can actually now start writing the boundary conditions. What happens when the position of the particle is exactly here, right? So then the probability is basically being absorbed by this boundary, right? So the probability should vanish, right? So I should write, so this P so if this is 0, right? So then I can also use this one over there, right? So now then this, you see that when I define the survival probability, right? So you see that we have integrated over x, right? So the survival probability is only a function of the initial condition, right? So the condition on survival probability will be the following. So you have at t is equal to 0, right? So if you are starting from inside, you always survive. So this is 1, right? And if you are starting exactly at this boundary, okay, so then this is 0. Which one? Tell me. Okay, so this one you understand, right? It's at the boundary, right? Now we also want to write some equivalent boundary conditions or initial condition for the survival probability, okay? Now survival probability is just the function of the initial condition, right? So this is the only variable I have. Now this x0, if it starts exactly at the boundary, right? So then of course it cannot come in. So then this is 0, right? It is immediately absorbed. There is no survival for this. But now at time t is equal to 0, if it starts somewhere, it's for finite x0, given that x0 is not exactly at the boundary. So at t is equal to 0, this is always found inside the boundary. So you can use this is the 1, okay? So these are like very trivial, conditions, but these are also like sort of like very important boundary conditions or initial conditions which we need to use multiple times. Okay, so if you remember, like I have defined now the fact that it takes some random time for this walker.searcher to go out of this boundary, out of this box, right? So this is given by the distribution, right? So we saw that there is a relation between this time statistics and also the survival probability, right? So that was, so ft t, right? And this is also again just the function of the initial condition, okay? This is given by t, okay? So this is mostly what we are doing. I'm trying to introduce this concept which I have done a bit before, but now more in the context of generic search process, okay? And these are the relations I want you to remember, like for the next class, okay? There is also, like another way to understand this, again by imagining that you have this process. This is our favorite illustration which we will do again and again, like, so again you have this random time, right? Within this random time, it basically comes from here to here, it gets absorbed. So you can use the same kind of analogy we had like starting of the class and show that this relation is satisfied, okay? Okay, so I think in the remaining remaining time, what I'm going to do is I'm going to use this relation, okay? And I'm going to write another relation for these, both the survival probability and the first passage time statistics, but in the Laplace space. And you will see that again, as in the case of transport properties or the position distributions, right, the Laplace formula was very useful, right? So similarly also you will see that this will be useful when we introduce the resetting. Okay. So if you take the Laplace transform on both sides, so you have e to the power minus st ft, this one, right? Okay, so if you do this, okay, and then you use these conditions, okay, which I have mentioned here, then what you will get is something like this, okay. So this is, so let's say this t is x naught. So this is the way I have, so this is simply the definition in the Laplace space. So instead of writing f something like this, f t s or something like that, okay, this is something also I could have written. Instead of that, I am using a slightly different notation, okay. So I'm just using this notation, or if you would like to write, you can also write it in this way. It doesn't really matter, but I will use mostly this notation. And then you have 1 minus q s, okay. So this is the way the first passage time statistics and the survivable probability is actually linked in the Laplace space. Okay. So now of course this is again, like you'll see that this is actually very useful. So then what we can do is we can actually switch between survivable probability and the first passage time, okay, in the Laplace space just by using this simple relation, okay. And then finally I would like want you to just note that if you want to calculate the mean time, okay, and the reason why I'm doing this bookkeeping calculation is because when we add resetting, okay, you'll see that this formulation, nothing will change actually. So all these things will be replaced by R, okay, because the definition, none of this definition, none of these relations, this actually will change. So once we do this, it will already set the stage for us for the when we introduce the resetting, okay. So how do we write the moment? Let's say the first moment or the mean first passage time. So you can just multiply with t, right? And just basically finish the integral. If once you do this, you will see that this actually has this following form. So this is q s is equal to 0 x naught. Okay. So this is also something we will use several times. So I think I have sort of like rushed quite fast in this last half an hour or so. So if you have any questions, please feel free to ask. Okay. 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 So I think what we have learned is that if you have some sort of a first passage process, there are a few random quantities or some statistical properties you are usually interested in learning. Okay. And these quantities are so-called survivable probability or the first passage time probability, okay. And from there, one can actually try to compute this time, mean first passage time, okay, and also the higher order moments, okay. So these are the some essential observables usually people are interested in understanding the first passage process, any kind of first passage process. Okay, so what I'm going to do is now let's just try to introduce resetting just like in brief. So let's say that I have this dynamics, right? And now in this dynamics, what happened is that I had this process and we let it, we let it go till the particle hit this particular boundary, right? So instead of doing that, now what we can imagine is something like this. So I'm going to just replicate this one. So let's say that I have the same domain, right? And now I have this escape route. Let's say I start from O. And now again I have a resetting clock, right? I have a resetting clock from outside, right? Okay. And now when that, like whenever a random time comes, I basically take the particle from here and instantaneously put it here, right? This is the way we did, right? Also for when we studied the spatial properties, right? And then again, like it starts from here, it does some motion like this, and maybe again another resetting event, and eventually, let's say it escaped from here, right? And then we will be interested in understanding how does the survival probability or the first passage time statistics, how these guys will change. So we have QR, T, X0, XR. So how this is the survival probability, and this will be the mean first passage time, okay? So how these quantities will change when we add the resetting, okay? This is something we would like to study, okay? So I think I still have like 10 minutes, but maybe I will just stop it today, okay? Because then I can sort of like start something fresh from tomorrow. Yeah. So we have like time, so you can start ask questions, or maybe we can start the tutorial a bit early. Huh? Okay. Yeah. Yeah.
This average of t as the Laplace transform of q, what could it physically mean?
What do you mean? Like,
I mean,
what
like
could
a
it be?
physical intuition. I mean, I don't know if this is a valid question. Or
So
not.
see, the survival probability is the probability that the particle stays inside this domain up to a given time, right? And now let's say that at some point of time it will start escaping, right? And this time is random. So you can calculate the statistics of this time, right? And the statistics of the time, the mean time of that is basically the mean first passage time, right? And you can write if you want to understand, so if f is the first passage time statistics, okay? So let's say that this, okay? So this is actually the number of paths, okay, that have escaped basically between time t and t plus delta t, okay? And from there you can try to write something like this. So as if the ones which didn't escape till t, and then at t plus dt, some of them escaped, right? So the change in that, something you can write it in this way. This is also another way to understand this. And obviously this is the guy, this is basically the entire statistics, right? And the mean time is just the first moment out of it. Okay? This is another way. So I think we learned like two or three different ways actually how to connect the first passage and the survival probabilities, right? Yeah. So I also like the approach of this, like the event happening, because in this case I actually do not need to care about my configuration space, like whether there is a particle or something. I mean, I can just define the survival probability and first passage times just in terms of the events, okay? And because this event, I mean, it's not that only the first passage process or search is happening only in the, only in position space. It could also happen in some other kind of random variables. So this is the reason you also should keep this schematic, this pictorial depiction of first passage process. So it will be easier, like at later stage.
Thank you.
Please.
So you were explaining how resetting the system stabilizes it
Right,
better.
right.
So in this context, in the context of this 3D random walker,
right.
So if I have a small opening, so let's say it's dV.
It's what?
Small opening
Yeah.
through which this random walker can go out. So suppose we have a V volume, and out of which suppose this dV is a little volume through which it can go out. So if so how resetting, because this origin now is arbitrary point for me.
It's arbitrary?
this origin is an arbitrary point for me. I could choose it
Sure,
anywhere.
sure.
So how now resetting will, so now stability in this term would be for this random walker to go out, is it?
No, so I will explain what is it. So the case when we basically study the stability, etc., when you do not really have any constraint in the phase space, in the sense that there is no absorption of the particles, right? The probability is always conserved, right? That is basically the context under which we studied the spatial properties, okay? Now, if we have something like this, when you have a leakage of probability, right? And yet, let's say that you keep on resetting and try to understand the position statistics, right? The position distribution of the particle. So what you will see that is, and obviously, you know, like because you have this, there is an exit. If you wait long enough time, the probability has to decay. Okay, so all the particles will eventually escape from this place. Okay, and now depending on where you put this guy and how far this guy is actually, the resetting location is from the target, depending on that, this relaxation will take place. But at very long time, you should not see any particle here. Because just because all the probabilities are eventually, you know, like getting lost through this particular domain. So there is, as such, it cannot stabilize, right? In this case, and the stabilization is not really the contextual word here. So resetting can maybe, depending on, as I said, depending on the distance, etc., it might hold the system longer inside, or maybe it can also help to go out. We'll see all these cases, you know, like in the next class or so.
Right. So, sir, as you said that depending upon where I'm resetting, the relaxation will differ.
No, not really relaxation, like the time it takes, basically, right?
So can we take the resetting and the point where it escapes the same place?
You want to keep this one here?
Yes, I'm just saying it. Like
so, you know, like then you, every time you reset, you going out. Yeah, of course. Like, in principle.
So I had a related question. So this boundary need not be closed, right? It could be just some.
Yeah.
So in that case, I guess you could get a. I mean, like in higher dimensions, it need not get absorbed, right? Because it's non-recurrent.
Right.
So in that case, you could have like what he's saying,
so
a steady state, even with the absorber.
Even with okay.
Right?
Yeah. So for example, let's imagine that the diffusion, 1D diffusion even, right?
It's recurrent, so it will always get absorbed.
It always will get absorbed, right? Yeah.
But in higher dimension, it need not get absorbed, I guess. Right?
But if you do resetting, right?
No, so without resetting, it need not get absorbed.
Without resetting,
but
it need not.
But even with resetting, it's not clear, like what.
So the point is that whether the mean time, even for the 1D case, right, the mean time is infinite, right? The recurrent probability is 1, but the mean time is diverging.
Right, yeah.
So then if you have a diverging mean, okay, even you have a diverging fluctuation, you can actually show that resetting indeed will have a finite, you know, mean time for you to reach the target.
1D I agree.
Even in a, like I'm talking about in actually a general sense, when I need not specify where from this mean and fluctuations are coming, not necessarily dimension based. I'm just putting the condition on the mean time and the fluctuation.
Right. Yeah, no, this I agree. But I'm saying like if it's not a closed boundary,
right.
Then you can get a stationary state even with an absorber, right?
Right. Because you know, like localized
absorber.
Right.
Okay, so I think there's few minutes if there are still some questions. Last minute question.
Arnav, like you were discussing about, like we were talking about that waiting time thing, right?
Right.
Yeah, I mean, like instead, I mean, the first one
yes,
made more sense.
Right.
But then, yeah, I mean, not that. Yeah, kind of that.
Yes.
But then, like, you came up with this formula where, like, you were saying, like, the probability density is, say, waiting time is, if waiting time is greater than R, then only, I mean, you will wait, you'll start waiting or something.
Right. You want me to repeat that part?
If
yeah, sure. So the idea is very simple, actually. So let's say that I define an event So I define an event, okay? So like only when A basically goes from, so system goes from state A to state B, right? And the question I asked that what is the probability that the system actually stays in state A up to time t? That was the question I asked. So it essentially means now for different realizations, right? This is a random variable. So this is coming from some distribution. So we'll have T1, T2, right? Many of them, IIT random variables, right? Now individually, whenever this time occurs, you always make a jump, correct? So if I want to understand the survival probability for the system to stay in here up to time t, so all individually these guys have to be greater than this observation time, right? Only then it stays back, right? So that is the reason I said the survival probability is nothing but t greater than this one. That is precisely the point, right? So all the random variables, these random variables ensures, right, that you essentially make a jump from here to here. But now when you put this condition, so it is guaranteed that you cannot make a jump, right, up to time t. So this is what the survival probability is. This is also another way to interpret this.